Is the universe a jigsaw puzzle that humanity has only just begun to assemble? The question settles like a stone dropped into deep water, rippling outward into layers of thought that are both thrilling and unnerving. It is not a question about finished pictures or tidy edges. It is a question about fragments, about the way a handful of irregular, time-worn pieces can suggest a larger image without ever quite resolving it. It is a question that opens rather than closes, that gives permission to be curious and to admit the scale of what remains unknown. Humanity has always told itself stories in pieces. A fossil here, a scattering of pottery there, the faint smear of microwave glow across the sky. Each new shard is a clue, a sliver of pattern. The first glance offers certainty. A corner piece fits, a cloud of hydrogen becomes a nascent star on a photograph. But the act of fitting one piece tends to make other missing pieces more glaring. The more is understood, the more the silhouette of ignorance takes shape. The puzzle grows not only in complexity but in appetite, producing new questions even as old ones are answered. There is a peculiar, almost contradictory emotion that accompanies this work. It is a mingling of triumph and unease. Triumph because a new piece, an isotope ratio decoded, a fossil dated, a map of distant galaxies, resolves a stubborn ambiguity. Unease because the resolution expands the frame of ignorance, showing more empty spaces where once there were only comfortable assumptions. The mind can be patient and ecstatic at once. Patient in the slow accretion of evidence, ecstatic in the sudden coherence when isolated facts click together into a larger shape. Yet beneath that exhilaration is the recognition that some gaps may be permanent, erased by the processes that govern planets and stars, erased by time itself. To understand why, it helps to treat the puzzle not as a static object but as a process of assembly performed on a surface that has been continuously reshaped. Earth is not a tidy table laid out for inspection. It is a palimpsest, a manuscript written and rewritten by forces that do not consult memory. Oceans rise and fall, continents collide and drown, fires consume, ice scours. Geological processes, weathering, subduction, metamorphism, do not merely obscure ancient artifacts, they rework matter at atomic scales, redistributed into forms that sometimes carry only the faintest hint of their original arrangement. A city can be swallowed by sediment and later folded into a mountain range, its stones liquefied into metamorphic rock. A coastline that once hosted thriving ports can be transformed into a cliff where no human footprint remains. In geological time, the act of preservation is rare, accidental, and capricious. This is where the metaphor of the jigsaw becomes both illuminating and limiting. It is illuminating because the human impulse to reconstruct, to identify patterns and narratives, is central to science. Archaeology, geology, paleontology, astronomy, and genetics all perform complementary acts of pattern recognition, combining disparate clues to form hypotheses about the past. It is limiting because the analogy implies that the pieces are discrete, well-defined, and available. In reality, the pieces are often smeared across contexts, partially obliterated, redistributed, or transformed into something else. A single grain of clay, chemically altered and transported by a river, might be the only surviving witness to an entire culture. The feeling that the more one knows, the more one realizes how much is missing, is not defeatist. It is the engine of inquiry. Each answer reframes the question, sharpening it. The discovery of DNA was not the last piece of the biological puzzle. It was a new way of asking how life arises, adapts, and sometimes disappears. The detection of the cosmic microwave background radiation did not complete cosmology. It provided a backdrop against which new anomalies could be measured, avenues for deeper inquiry opened. The map of human migration created from genomes did not finalize the story of humanity's past. It introduced complexities of exchange, admixture, and cultural transformation that demand explanation. Consider for a moment the way time itself is compressed in human thought. To speak philosophically about deep time is to rearrange the mind's measures. A common conceit helps: if Earth's entire history were compressed into a single year, humans would appear for roughly the last few seconds of December 31st. Dinosaurs would dominate a span tens of millions of years long. Continents would drift, collide, and reshape the face of the planet in epochs. Languages would rise and fall like brief seasons. Geological processes that build and destroy leave impressions in the rock record, but those impressions are biased. They are better at preserving dramatic events, sudden volcanic eruptions, mass extinctions, than the slow, cumulative labor of ordinary daily life. A civilization that flourished for a few millennia under benign conditions might leave almost no trace when scaled against the whole of planetary time. The idea that advanced cultures could have existed and been erased is not an invitation to fancy. It is an invitation to humility. Preservation is contingent. Organic materials decay, wooden structures rot, metals corrode, ceramics shatter and are reused. Erosion can redistribute the very sediments that once contained artifacts. Plate tectonics can bury and transform. Over millions of years, the stratigraphic record is punctuated by gaps, unconformities where whole chapters are missing. Those gaps are not anomalies to be explained away. They are the natural consequence of a dynamic planet. To assert that absence of evidence equals evidence of absence is to misunderstand the mechanisms of loss. Science proceeds by recognizing patterns in incomplete records, by developing models that can account for both what is preserved and what is not. It calibrates expectations against the bias of preservation. For example, the archaeological record of coastal societies is particularly precarious because sea levels rise and fall. Shorelines today may be kilometers away from where they were 10,000 years ago. A thriving littoral community could be submerged, its features pulverized by tides and currents. Evidence that could confirm complex social organization might be distributed in scattered, inaccessible contexts, submerged sites, deeply buried in river deltas, or transformed beyond recognition by mineralization. The absence of standing ruins is therefore not conclusive proof that complexity never existed. Rather, it suggests that the processes of preservation are decisive and often unforgiving. This is not to say that any speculative assertion is equally plausible. Scientific inference is an economy of plausibility constrained by known processes. Hypotheses must align with the mechanics of decay, with thermodynamics, with geophysical realities. The methods that reconstruct past worlds, radiometric dating, stratigraphic correlation, comparative anatomy, isotopic analysis, are instruments finely tuned to discern subtle signals. They are also instruments that reveal their own limits. Radiometric clocks are powerful but can be reset. Isotopic signatures can be ambiguous. Stratigraphic contexts can be disturbed. Each technique adds a piece to the puzzle while also exposing the seams where assumptions are made. There is, then, a particular kind of emotional cadence that accompanies scientific work on deep time. It is a rhythm of dawning clarity followed by recursive doubt. One moment reveals a small, bright fit, a fossil reclassified, a stratum dated, an astronomical signal characterized, and the next moment reveals more empty space where the mind, now sharpened by context, recognizes that it does not yet understand the larger picture. This is not failure. It is the shape of honest inquiry. In the glow of discovery, scientists feel both elated and chastened. They feel the intimacy of connection to a past that is not theirs, and they feel the weight of all that has been burned, eroded, or otherwise removed from the ledger of things. That tension is part of what makes the enterprise of understanding so human. It produces stories that are at once tentative and grand. It fosters a kind of shared humility that is rare in other domains of human thought. The recognition that any conclusion might be provisional does not weaken the desire to know, it intensifies it. There is a beauty in approaching a partially assembled puzzle and appreciating how the patterns point beyond themselves. The incomplete image becomes an invitation rather than a frustration. One of the most productive responses to the gaps is not a desperate attempt to assert completeness, but a methodical effort to expand the kinds of evidence considered. New techniques become new modalities of seeing. A microscope can reveal microwear in a tool that indicates how it was used. A mass spectrometer can detect trace organic compounds that hint at diets. Satellite imagery can reveal rectilinear foundations buried beneath vegetation. The puzzle grows horizontally as much as vertically. It demands not only specialized insight, but integrative imagination, the ability to place geological processes beside cultural inference, to read climate proxies alongside technological signatures. The task is interdisciplinary because the world itself does not respect disciplinary boundaries. Equally important is the ethical dimension of reconstruction. The impulse to assemble the past must be tempered by an awareness of what is at stake in narrating lost worlds. Interpretation can become an instrument of power, privileging certain narratives or erasing others. The most responsible approach acknowledges that reconstruction is always partial, that it is framed by present assumptions and values. The aim is not to achieve a final, authoritative account, but to produce credible, testable models that invite correction. This humility does not imply epistemic paralysis. Rather, it formalizes uncertainty as a scientific resource, a condition to be quantified, not a rhetorical device to justify speculation. There is a kind of paradoxical consolation in accepting permanent incompleteness. To live with the knowledge that some pieces are irretrievably lost is to practice a long-term modesty about human claims to knowledge. It frees inquiry from the demand to be exhaustive and focuses it on coherence and plausibility. It encourages a kind of prose that is open-ended, an intellectual posture that delights in the work yet recognizes its limits. For the public that listens to such narratives, whether in a long-form video, a museum exhibit, or a lecture, there is a moral and aesthetic lesson. That curiosity, humility, and patience can coexist, that the unknown is not a failure of intelligence, but a frontier. There is also, inevitably, an emotional landscape that attends the idea of a universe of missing pieces. For some, the notion that entire chapters could have been erased by time induces vertigo. It flattens familiar certainties and forces a reckoning with human temporality. For others, the same notion is liberating. It renders our present moment more precious, our efforts more heroic, knowing that each act of discovery is an act of recovery against oblivion. The political and cultural stakes of this recovery are not trivial. Reconstruction of the past shapes identities, informs stewardship of heritage, and guides decisions about conservation and research priorities. What is chosen to be investigated, preserved, or displayed is a function of what a society values. The puzzle thus becomes a social as well as a scientific project. In the end, the jigsaw metaphor is a useful opening image because it situates the work of understanding within a structure of assembly, pieces, edges, fits, while simultaneously inviting a deeper appreciation of the forces that create and destroy those pieces. It foregrounds the interplay between discovery and loss, between knowledge and its limits. It illuminates the duality at the heart of inquiry, that finding one thing often exposes the shape of what remains elusive. The horizon of that elusiveness is not an empty abyss, it is a landscape replete with new questions. What patterns can be inferred from the fragments that remain? How do processes of preservation bias the record? To what extent can novel technologies expand the archive of what is discoverable? How should humanity balance the zeal for discovery with the ethics of interpretation and conservation? These are not rhetorical questions meant to end the conversation. They are invitations. They are the first frames of a longer narrative, a serialized exploration that will examine the mechanics of preservation, the kinds of evidence that survive deep time, the ways in which modern science reconstructs a lost past, and the speculative edges where reason meets imagination. Each subsequent installment will take a particular set of pieces, from microscopic biomarkers and sedimentary layers to planetary dynamics and the faint signatures of cosmic phenomena, and will ask how they align, contradict, or complicate one another. For now, the opening question remains, is the universe a jigsaw puzzle that humanity has only barely begun to assemble? The tentative answer is both yes and no. Yes, in that there are countless fragments, each conveying a sliver of narrative, each a legitimate cause for wonder. No, in that puzzle suggests completion that may never exist. The more apt image might be a constellation of fragments floating across a vast dark field, some luminous enough to guide inquiry, others dim smudges that hint at shape but resist full resolution. The project of understanding is to map that constellation, to describe its geometry, to measure the light of each element, and to keep asking what patterns might emerge when millions of small truths are brought into relation. The human impulse to assemble, to understand, to narrate endures. With every new tool, every new observation, humanity has built bridges across time. Each bridge reveals not only where it reaches, but the chasms that remain. That dual vision of bridges and chasms is the true engine of curiosity. It keeps the hands at the table, the eyes scanning the pieces, the mind patient and ravenous. It is a mode of engagement that respects the scale of deep time while refusing to be intimidated by it. So the puzzle sits on the table of human thought. Pieces glint. Some fit, some do not. New pieces arrive with the steady, inexorable work of research, and with each fit comes the quiet, invigorating recognition that the more assembled, the more the gaps are revealed. In the spaces between the pieces live the mystery that calls the next generation of inquiry, promising that the story is not yet finished, only richer, stranger, and more compelling than the first glimpse had allowed anyone to imagine. What image can hold the beginning of everything? The question arrives like a shadow at the edge of a map, an outline labeled with a name that is both triumphant and frustrating, the Big Bang. It is a corner piece of the cosmic jigsaw that gleams with successful explanation. It accounts for the steady expansion of space, for the observable cooling of the universe, for the cosmic microwave blow and the relative abundances of hydrogen and helium. Yet it leaves an even more intoxicating vacancy in its wake. The space, the thought, the gnawing question of what, if anything, lay before that astonishing event. The Big Bang explains the expansion. It does not explain the origin of the rules that allowed it to expand. The story of the Big Bang is, in many respects, the story of discovery itself. Astronomy mapped the redshift of distant galaxies and revealed a cosmos that is receding like a tide. Radio telescopes registered an omnipresent whisper of microwaves, the afterglow of an epoch when the universe became transparent. Roughly 380,000 years after the initial hot phase, nuclear theory matched the absurd ratios of light elements formed in the first minutes. These empirical fits, each a clean cut in a ragged puzzle, gave modern cosmology its backbone. They made the Big Bang not myth, but inference. They turned an idea into a narrative scaffold capable of hosting testable predictions. Yet precision only sharpens absence. When general relativity is extrapolated backward, space-time curves into an extreme, a point where density and curvature diverge. Physicists call it a singularity, a breakdown of the equations that frame gravity, time, and space. In that mathematical collapse, the language of cause and effect falters. The Big Bang, as usually described, becomes less an event that can be inspected than a signpost that says, "Here our current theories stop applying." It is a boundary on the map where the compass spins and familiar landmarks vanish. There is an emotional cadence to this boundary. It produces exhilaration and vertigo in equal measure. The exhilaration is the recognition that the universe obeys patterns, that its infancy can be read from the faint fossil light that suffuses the sky. The vertigo is the sense of limit, that some origins may be hidden by the very laws that describe them. For those who study deep time on a cosmic scale, the vertigo is not raw nihilism, but a sober prompt to ask new kinds of questions and to invent new kinds of measurements. Among the most consequential innovations of the late 20th century was the idea of inflation, a phase of exponential expansion that, in fractions of a second, stretched microscopic quantum irregularities to cosmic scales. Inflation solved problems that had nagged cosmologists for decades: the near uniformity of the cosmic microwave background across regions that would otherwise never have been in causal contact, and the apparent flatness of space-time on the largest scales. Where simple extrapolation produced paradoxes, inflation provided a mechanism. It painted the early universe as an engine of amplification, turning quantum noise into the seeds of galaxies. But inflation, too, is double-edged. If inflation occurred as theorized, it transformed the earliest information into our present structure by stretching and smoothing. That process erases many traces of what preceded it. The rapid expansion acts like a cosmological sander, wiping fine-grained features from the face of space-time. In this sense, inflation explains visible uniformity by design. It intentionally hides earlier conditions. It preserves some signals, the spectrum of primordial fluctuations, subtle statistical fingerprints, but it silences a great deal. The result is familiar in the study of geological records on Earth. Events that leave dramatic, unmistakable layers are more likely to be preserved than the soft, gradual histories that disappear under relentless change. If inflation is a broom sweeping prehistory clean, other theoretical frameworks propose different outcomes. Quantum cosmology, string theory landscapes, cyclic models, and variants of bouncing universes each offer visions that push the question of before into different territories. In some proposals, our expanding bubble arose from a pre-existing vacuum or from the decay of an energetic field. In others, a prior contracting phase reached a high density and rebounded in a bounce, giving birth to the current expansion. Some ideas place the Big Bang as one episode in an immense multiverse, countless pocket universes nucleating within a vast inflating space-time. Each scenario reframes the Big Bang from an absolute beginning into a transition, an interface where one regime hands over to another. These speculative frameworks carry with them moral and epistemic obligations. The mind can be dazzled by the plurality of models, as if theoretical fecundity alone were evidence. But science is an economy of constraint. For hypotheses to be meaningful, they must make contact with observation, however subtle the contact. What observational relics could betray a pre-Bang history? Cosmologists have been remarkably imaginative and disciplined in answering that query. Primordial gravitational waves are among the most cherished messengers. Unlike matter and light, gravity interacts weakly with other fields and can carry signals from epochs otherwise opaque. Inflationary models predict a stochastic background of gravitational waves that could imprint a distinct twist in the polarization of the cosmic microwave background, a B-mode pattern. Detecting such modes would be akin to hearing the faint ringing of a cosmic bell struck in the universe's infancy. their amplitude and spectrum would constrain the energy scale of inflation, and might distinguish between a simple inflationary burst and models where pre-inflationary dynamics matter. Conversely, the absence of the predicted signal would rule out many scenarios and guide theorists toward new physics. Topology offers another avenue. If space has a non-trivial topology, if it were finite in some directions or contained subtle identifications, then the cosmic microwave background could contain repeated patterns or matched circles. Those signatures would be the fingerprints of a global geometry that predates or constrains the early expansion. Similarly, departures from the exact statistical properties predicted by simple inflation, such as specific types of non-Gaussian correlations in the microwave background, could reveal interactions or antecedent structures. Even relic particles, stable, weakly interacting species that survive from primordial times, could be evidence of physics before the traditional hot Big Bang. The cosmic neutrino background, barely within the realm of detectability, is one such ghostly archive, and hypothetical heavy relics might populate the dark matter that shapes galaxy formation. Yet, with every plausible messenger, there is a counterpart of erasure. Inflation smoothing in our observational horizons, the limit of the region from which light has had time to reach us, conspire to confine accessible signals. The finite age of the universe makes the observable cosmos a spherical island. Beyond its shores may lie whole expanses forever inaccessible to direct measurement. If the relevant pre-bang mechanisms were confined to scales larger than our observable patch, they would leave no local trace. The situation is a precise analogue of archaeological recovery on Earth. Some events are so geographically or temporally separated that their traces never survive in the sampled strata. Beyond empirical constraints, there is a deeper conceptual impasse. The language of time itself is under scrutiny when considered at the boundary of cosmological theories. In quantum gravity programs, time may be emergent rather than fundamental, a derived parameter that emerges from degrees of freedom more primitive than classical space-time. If time is not a fundamental backdrop, asking what came before may be a category error. The born of an expanding space-time might be the formation of time as an operative construct. Before that, there was no before in any meaningful sense. This move reframes origin narratives, but also shifts them from testable conjecture toward metaphysical interpretation. A move that both thrills and alarms those seeking a scientifically anchored account. The emotional tenor here is complex. For those enthralled by the sublime, the possibility that time itself could be emergent turns the cosmos into a theater of radical novelty, laws and structures, arising from a deeper substrate in a manner that can be studied, modeled, and constrained. For others, the idea introduces an unsettling contingency that deep questions about causation and beginning may lie beyond empirical reach. The tension is familiar to anyone who studies pasts erased by time on Earth. There is a humility in both cases, in accepting that certain origins might be forever out of observational reach, and in designing experiments that press against that boundary with the tools available. There is a human rhythm to the search. Telescopes peer, and data accumulates in petabytes. Probes and satellites sweep the sky. Interferometers listen for the hush of space-time ripples. Particle detectors search for relics in subterranean caverns. Each experimental advance refines the map of what is plausible. Non-detections close corridors of theory that once seemed wide open. Tentative signals illuminate narrow paths that demand confirmation. The history of cosmology is a disciplined back and forth, where mathematical ingenuity proposes structures and instrument builders test them with instruments of increasing precision. And yet, as with the archaeological imagination applied to planetary deep time, there exists a fertile middle ground between dogmatic skepticism and unmoored speculation. It is the practice of constructing models that are both imaginative and falsifiable, of laying down predictions that could be, at least in principle, contradicted. The merit of multiverse conjectures or bounce models is not merely in their narrative appeal, but in whether they suggest signatures one day within observational reach. For example, collisions between bubble universes in some eternal inflation scenarios could leave azimuthal temperature, anisotropies in the cosmic microwave background. A statistically significant detection would transform an abstract landscape into an empirical claim. The converse is true as well. The failure to detect expected imprints refines theory, pruning extravagant branches and sharpening the core. Philosophically, the question of a before nudges civilization toward a broader existential stance. If the Big Bang is not an ultimate beginning, then human time is nested within cycles or multitudes whose scales dwarf not just lifetimes but entire civilizations. This nesting feeds a paradoxical mixture of insignificance and meaning. Insignificance, because individual human concerns are tiny within a cosmological sequence that might include infinite iterations. Meaning, because curiosity itself becomes the act by which a small intelligence reaches outward to comprehend structures of grand scope. The narrative shifts. Human inquiry is not merely about reconstructing the past for its own sake, but about participating in the cosmos's self-interpretation. The predicament also imposes an ethical subtlety. Much as archaeologists prioritize context and avoid overeager storytelling that projects present values onto vanished peoples, cosmologists must resist a similar temptation to reify mathematically appealing models as truth without stringent checks. The proper posture blends ambition with restraint. The task is to craft narratives of origins that are generous enough to entertain bold possibilities but disciplined enough to admit the rigor of falsification. Finally, the mystery of before the Big Bang is a testament to how scientific narratives progress, not through single monolithic revelations, but through an accretion of constraint, imagination, and patience. Each experiment, each theoretical advance, is a small lamp cast into a cavernous space. Sometimes the lamp illuminates a salient shard that answers a narrow question. Sometimes it reveals only more emptiness, prompting new questions. Both outcomes are progress. The cosmos resists finality, and science thrives in that resistance. The Big Bang remains both anchor and veil. It anchors an account of how the observable universe became what it is. It veils the prehistory that might have been, or the deeper laws from which space and time themselves emerged. The search for what preceded the Big Bang is as much an exploration of the limits of human knowledge as it is an attempt to fill a missing fragment in a cosmic jigsaw. The questions posed are precise and audacious. Did something precede the bang, and if so, what fingerprints might it have left? Is the origin singular or episodic? Is time fundamental or emergent? Each answer will reshape not only academic maps, but the metaphors used to situate human meaning in the face of deep time. In that way, the inquiry into cosmic origins is an extension of the same humility urged in the study of vanished civilizations and erased records on Earth. Both endeavors confront processes of erasure and contingency. Both require integrating multiple strands of evidence and confronting the limits of preservation. The difference is scale. The universe's time span and energies dwarf terrestrial examples, but the epistemic posture required patience, methodological rigor, and an embrace of uncertainty as a productive state is the same. So the question remains open and luminous. What, if anything, lay before the Big Bang? The best answers so far are partial bridges, theoretical constructs constrained by a patchwork of observational data, experiments poised to test the faintest echoes from the earliest epochs, and a philosophical readiness to admit that some questions might reconfigure themselves when viewed through new frameworks of physics. The image is not of a single piece missing from a table, but of an entire frontier, a vast dark field containing countless potential fragments, some of which may never be within reach, and others that await the patient labor of discovery. The project of understanding continues, one careful measurement at a time, with the humility that comes from appreciating both what has been explained and the deep, persistent mystery that remains. Will the universe stretch on like an unending horizon, fold back into itself like a closing hand, or tear apart in a final, violent unraveling? That question arrives as a different kind of edge on the cosmic map, not the edge of origin, but the edge of destiny. It presses a single intimate demand. What will become of the grand, slow story that began in a dense, hot state and has, across eons, fashioned galaxies, stars, planets, and the brief flicker of minds that ask such questions? The discovery that space is not merely expanding but accelerating transformed the problem of cosmic fate from speculative metaphysics into an empirical puzzle. Supernovae observed in the late 20th century spoke with a clarity that surprised the world. Distant explosions were dimmer than expected, implying that galaxies were receding faster with time. An invisible driver, dark energy, was inferred, something permeating space that behaves unlike ordinary matter or radiation. Its presence altered the calculus of the universe's end. No longer was the future determined solely by how much mass gravity could muster. The character of dark energy held sway. To imagine the endpoint is to imagine the tug-of-war between attraction and repulsion on cosmological scales. On one side, gravity gathers, matter draws matter, galaxies cluster, black holes swallow. On the other, dark energy pushes, it stretches the metric of space itself. The crucial question is not just whether the universe expands now, but how the force behind that expansion behaves as time stretches forward. Subtle differences in that behavior lead to profoundly different narratives. One plausible and presently favored outcome is the slow, relentless cooling known as the Big Freeze or heat death. If dark energy is a cosmological constant, an unchanging property of empty space, the expansion will continue forever, accelerating but becoming asymptotically steady in its effect. Galaxies beyond bound clusters will recede faster than light and slip beyond the observable horizon. Over tens to hundreds of billions of years, star formation dwindles as interstellar gas is exhausted or locked into long-lived faint stars. Galaxies coalesce into larger, quieter structures, collisions become gentle mergers of fossilized systems. The vibrant cosmic web fades into isolated islands of matter separated by ever-growing gulfs of dark, cold vacuum. The passage of time can be measured in human-scaled metaphors, but the scales here are astronomical in both senses. Red dwarf stars, the patient embers of stellar evolution, will persist for trillions of years, offering a dim, prolonged twilight. Beyond that, stellar evolution grinds on toward a degenerate era. White dwarfs, neutron stars, and black holes remain, relics of a bygone luminous age, on timescales of 10 months 14 to 10 years. Collisions between brown dwarfs and the slow decay of orbiting systems will leave increasingly sparse traces. If protons are unstable, their decay, hypothesized by some grand unified theories, would slowly disassemble baryonic matter, itself on timescales that might exceed 10 next 34 years. Should that decay occur, atoms become ephemeral, chemistry collapses, and the intricate scaffolding that supports life and civilization unravels. Then comes a black hole era, gravity's last monuments. As galaxies merge, matter sinks into a few dominant black holes, which themselves become the last repositories of coarse-grained structure. Hawking radiation will, imperceptibly but inexorably, erode these titans over stupendously long times, perhaps 100 years for the largest black holes. They will evaporate into a thin bath of low-energy quanta. After their disappearance, the universe, insofar as structure is concerned, will be a cold, dilute sea. Photons stretched to wavelengths beyond imagination, particles spaced so sparsely that interactions are rare. Entropy will have crept toward a maximum. Available free energy, the thing that powers complexity and therefore life, will be exhausted. This picture, austere, quiet, almost ascetic in its finality, is consistent with a universe governed by thermodynamic imperative. Energy gradients dissipate and equilibrium reigns. A different, less placid possibility is the Big Rip. This scenario requires a form of dark energy, more exotic than the cosmological constant, a phantom energy whose density grows with time. If the equation of state parameter WA ratio that characterizes pressure to energy density dips below 1, repulsive effects strengthen as expansion proceeds. The scale factor, the measure of cosmic size, can then diverge in finite proper time. The sequence of destruction in a Big Rip is almost theatrical in its chronology. Galaxies dissociate, gravitational bindings fail, star systems unravel, planets are torn apart, atomic bonds break, even nuclei. And finally, space-time itself could be rent asunder. The universe would end not in a cold silence, but in a crescendo of structural disintegration, a catastrophic singularity of expansion. For those who conceive the cosmos as a long, patient narrative, the Big Rip is an abrupt, violent epilogue. Between these extremes stands the possibility of eventual collapse, the Big Crunch. If dark energy is not constant but dynamic, it may decay or reverse sign. Some theoretical models allow dark energy to diminish and become gravitationally attractive on long timescales, allowing mutual gravitation to reclaim the expansion. In that case, the cosmos would slow, halt, and begin to recontract. Structures would draw together, temperatures would rise. The end would mirror. In reverse, the early hot state, compression instead of expansion, concentration instead of dilution. If the contraction continued to a singular point, classical physics would again break down, and the narrative would end at a boundary where our equations fail to apply. The symmetry of such a fate is seductive in its aesthetic logic. What begins in density may end in it. It also raises practical questions about information, entropy, and whether any memory of the prior eon survives such a collapse. Yet another suite of outcomes belongs to cyclic or bounce cosmologies. In these frameworks, the Big Bang is not unique, but episodic. The universe could undergo an endless sequence of expansions and contractions, or it could bounce from a contracting phase into a new expansion without ever encountering a true singularity. Models vary. In some, collisions between higher dimensional branes and string theoretic landscapes trigger new cycles. In others, a scalar field called quintessence governs a slow contraction that rebounds into expansion, with entropy somehow reset or diluted between cycles to allow the reemergence of structure. The emotional appeal of cyclic models is profound. They offer a kind of cosmic rhythm, an eternal music of rise and fall. They also invite hard questions. How, precisely, is entropy managed across cycles? How does information persist or vanish? Are the initial conditions of each cycle independent, or does some drift accumulate? There are speculative, mathematically fascinating proposals that attempt to reconcile observed acceleration with long-term recurrence. Roger Penrose's conformal cyclic cosmology, for instance, posits that the infinite, dilute future of a universe with a positive cosmological constant can be conformally mapped onto a new Big Bang. In that mapping, the physics of very low energy, effectively scale-free states is reinterpreted as the seed of a new eon. The idea is audacious and elegantly conceptual, but it demands both mathematical leaps and testable imprints. Advocates point to possible signals, unusual imprints in the cosmic microwave background, but the evidence remains contested. The history of cosmology teaches caution. Mathematical beauty alone does not guarantee physical truth. What lends weight to any of these narratives is observation. The current data, cosmic microwave background measurements, galaxy surveys, supernova catalogs, and baryon acoustic oscillation studies are consistent with a cosmological constant within observational bounds. The best fit value of W hovers very close to 1, with uncertainties at the percent level. That central value implies a future in which expansion continues forever, leading to isolation, gradual cooling, and the long, entropy-driven decline towards heat death. But slight deviations matter. An apparently small departure in W today could signal qualitatively different futures billions or trillions of years hence. The project of cosmology, then, is to refine measurements, tighter constraints on W, its time dependence, and the possible detection of novel signatures such as primordial gravitational waves, imprints of bubble collisions, or relic particles that would betray new physics. The stakes are not merely academic, they are metaphysical in the classical sense. The universe's long-term topology, its thermodynamic destiny, and the possibility of recurrence all hinge on such empirical subtleties. There is a poignant parallel between questions about deep time preservation on Earth and questions about cosmic destiny. Just as tectonics, erosion, and chemical transformation erase the traces of ancient civilizations from the planet's surface, the dynamics of expansion and entropy erase the structural legibility of cosmic history. As the cosmos proceeds toward heat death, future observers in far distant epochs will find different evidence than humanity finds today. Cosmic microwave background red-shifted into oblivion, galaxies merged into monochrome halos, chemical complexity depleted. The record of what once happened, the luminous era when stars burned and galaxies shone, will become invisible. The loss of diagnostic evidence is not merely an academic loss, it is a philosophical one. It implies that the ability to reconstruct, to infer, to narrate past aeons is time-dependent. There are eras in which cosmological archaeology is straightforward and eras in which the archive is largely erased. That fragility of evidence is a sobering mirror to the terrestrial observation that civilizations can be erased by geophysical processes. It deepens the humility with which cosmic narratives must be spoken. Beyond the empirical and the poetic lies the question of meaning. If the universe ends in a slow, inevitable cooling, what does human curiosity amount to? If it crashes in a hot collapse, is every story fated to be crushed? If it cycles, does continuity persist across eons? These are not new anxieties. Cosmological destiny has always been a neighbor to existential reflection. The scientific response is not to promise consolation, but to provide clarity. The fate of the universe does not determine the value of finite acts, it frames them. In some sense, the awareness that cosmic drama plays out on scales vastly larger than human lifetimes magnifies the modest heroism of curiosity. The hands that measure, the instruments that listen, the minds that model, these are ways to extend narrative beyond immediate survival, to participate in a collective enterprise of comprehension that spans generations. Practical questions arise, too, about the limits of survival and preservation. Speculative thinkers ask whether any structure could persist across extreme futures, whether information could be encoded in ways robust to proton decay or gravitational dispersal, whether intelligence could harness black hole evaporation for computation or energy. These are exercises at the edge of physics and philosophy, creative, suggestive, but tethered to the hard constraints of thermodynamics and known interactions. They illuminate human ingenuity under the pressure of temporal finitude, but remain, for now, tentative thought experiments rather than engineering blueprints. What does all this imply for inquiry in the present? It implies an ethic to refine measurements, to pursue anomalies rigorously, to invest in instruments that test the time dependence of dark energy and the properties of gravitation on the largest scales. It also implies narrative humility, to offer accounts that recognize both what is tightly constrained and what remains open. The future is not a single inevitable landscape revealed in advance. It is a set of possibilities whose probabilities are informed by observation and whose contours reward imagination tempered by discipline. The end of universe question, like the question of origins, presses humanity toward an attitude of patient, rigorous wonder. It asks for a kind of intellectual courage, the willingness to accept that answers may be partial, that our best models may be provisional, that some features of cosmic fate may remain forever beyond the observational horizon. Yet within that admission is a powerfully human affirmation. That curiosity persists even when the object of curiosity is the most immense and indifferent of stages. So the saga of cosmic fate continues as another chapter in the larger project sketched earlier to assemble fragments, build constraints, and narrate responsibly. Whether the universe dwindles into cold uniformity, rips itself apart in a final spasm, rebounds into another cycle, or collapses into a hot reunion, the work of discovery remains the same. Telescopes must probe, theoretical work must sharpen, and the human capacity to hold awe alongside skepticism must endure. The concluding images are not of theatrical finality, but of a long, disciplined labor, mapping probabilities, chasing subtle signals, and acknowledging that some answers will alter not only scientific charts, but the metaphors by which humanity situates itself in the vast geography of time. In the silence between the present and any final state, a question endures, not as a question easily answered, but as an invitation. It is an invitation to listen more closely to the faint murmurs of the cosmos, to refine instruments and argument, and to practice an intellectual modesty born from recognizing that origins and endings alike are shaped by processes that can erase evidence, obscure causation, and challenge intuition. The future of the universe is a problem whose contours are traced by observations and imagination in equal measure. Its study is an act of stewardship for knowledge itself, a commitment to bearing witness as best as beings of a single epoch can. What if the majority of the universe were a thing that could never be touched, never seen, never tasted, and yet that thing held the cosmos together? The question sits like a private astonishment. More than 4 times the mass of all the stars, planets, gas, and dust combined, an invisible substance shapes the grand patterns of space. It is a mystery that feels like finding an architectural blueprint with most lines drawn in ultraviolet. The outline of a house is apparent, the material of the beams is not. The evidence arrives in simple, stubborn facts. Watch a spiral galaxy rotate, and the outer arms refuse to slow in the way Newtonian expectation predicts. The gas and stars at the edges should orbit more slowly than those closer to the bright center. Instead, they move as if an unseen halo supplies extra gravity. Point a telescope at the night sky, and massive clusters of galaxies produce gravitational lensing. Starlight is bent by far more mass than what the visible galaxies can account for. Map the cosmic microwave background, and the fine ripples in that ancient glow reveal a universe whose large-scale clumping requires more gravitational heft than ordinary atomic matter can provide. Run numerical simulations seeded with the laws of physics, and only with extra, non-luminous mass do the intricate filaments and voids that astronomers observe naturally emerge. The cosmos behaves like a scaffold built from something that does not record light. Those observational threads weave into a compelling portrait. There is mass that responds to gravity but does not interact, or interacts only feebly, with the electromagnetic forces that make light possible. The community of scientists does not anthropomorphize the dark. Instead, they have collectively accepted a practical name and a practical problem. how to characterize and, if possible, detect the nature of this darkness. The popular image of dark matter is of a vast halo cloaking galaxies, an invisible fog that lets the luminous parts float. That image is useful, but it understates the subtlety of the role. Dark matter is not only a cloak, it is the stage upon which the luminous actors assemble. In the earliest moments after recombination, when the universe cooled enough for electrons and protons to combine into neutral atoms and for photons to stream freely, ordinary matter was tightly coupled to radiation. Dark matter, if it existed then as a non-relativistic, weakly interacting component, was already clumping under gravity. It drew baryons toward its wells. Those concentrations seeded the formation of the first galaxies and set the pace of structure formation. Without that invisible scaffolding, the universe would have been a far thinner, more featureless place for much longer. Stars might have formed late or sparsely, changing the narrative for any future planetary chemistry and life. In this way, dark matter is not marginal. It underwrites the cosmic architecture across deep time. Yet the question of what dark matter actually is sits at the edge of instruments and theory. Two broad families of answers have been pursued. The dark is a new form of matter. Novel particles or compact objects, or the laws of gravity themselves must be revised at large scales. Both directions are fraught with technical complexity, philosophical implications, and long histories of partial success and stubborn failure. On one side stands particle dark matter. This family includes several candidate classes, each invoking a different kind of particle with different masses and interaction strengths. Weakly interacting massive particles, or WIMPs, were for decades the poster children. They elegantly fit particle physics extensions to the standard model and produce the right relic density if frozen out in the early universe. If WIMPs exist, they should occasionally interact with ordinary nuclei. That expectation drove the construction of detectors deep underground. Vast vats of noble liquids chilled and shielded below rock to avoid cosmic rays. Sensors tuned to record the faintest recoil of a nucleus struck by something almost ghost-like. It is an image of patient listening, a subterranean lake of xenon or argon, electronics humming, data streams arriving in columns and rows, nights of cross-checks to eliminate mundane backgrounds. Decades of searching delivered a stream of null results. Each non-detection narrowed the range of plausible interaction strengths and masses, pruning hopeful parameter space. The emotional rhythm here is familiar, a flutter of excitement at sensitivity milestones, disciplined disappointment when backgrounds masquerade as promise, and the stubborn optimism that drives larger, quieter detectors deeper into the earth. Axions offer a different technical poetry. These hypothetical, extremely light particles would not cloud a nucleus, but instead would convert to photons in the presence of a strong magnetic field. The detection strategy is conversely delicate, a resonant cavity bathed in cryogenic silence, tuned to a frequency that would coax an axion into surrendering a whisper of microwave energy. The search is narrowband and patient, scanning frequency by frequency across decades of possible masses. The emotional texture here is like tuning an antique radio, waiting for a single, meaningful static to blossom into a signal. Then there are heavier, more exotic possibilities, sterile neutrinos that mix faintly with known neutrinos and might decay to produce X-rays, or primordial black holes formed in the early universe that survive as compact, non-luminous point masses. Each candidate demands a different detection strategy. X-ray telescopes scouring galaxy clusters for an unexpected emission line. Microlensing surveys watching distant stars for brief brightenings when an invisible compact mass passes in front. Each non-detection, or each ambiguous hint, shifts the emotional landscape. Hopeful anomalies are examined. Often found wanting under scrutiny, models adjust and diversify. On the other side of the conceptual divide stands modified gravity. The idea is both pragmatic and radical. Perhaps the equations that relate mass to gravitational acceleration are incomplete at galactic or cosmological scales. Modified Newtonian dynamics, or MUND, proposed a simple empirical change. Below a certain acceleration scale, the effective gravitational pull is stronger than Newton's law would predict. With that tweak, many galaxy rotation curves can be reproduced without invoking an invisible mass component. There's an elegance to this approach. Fewer unseen entities, more modification of law. But the gains are uneven. Mund-like theories reproduce certain galactic phenomena beautifully, yet struggle with galaxy clusters and with the fine structure in the cosmic microwave background. Moreover, the most persuasive argument against radical modifications of gravity as the whole story comes from observations of colliding galaxy clusters. In some of these collisions, the hot, X-ray emitting gas, which carries much of the baryonic mass, is slowed and displaced by drag, while the gravitational potential traced by lensing appears to follow the galaxies, not the gas. The simplest interpretation is that most mass is in a collisionless component, which passes through. This behavior favors particle dark matter over a pure gravitational tweak. Even so, the debate is not absolute. Hybrid models exist where both new fields and particle species contribute, and theorists continue to explore frameworks that might reconcile cluster-scale lensing and galactic phenomenology. The scientific ethos is clear. Favor frameworks that explain more observations with fewer ad hoc assumptions, but remain open to creative reworkings when data demand it. There is another layer of emotional resonance when considering how little direct interaction dark matter appears to have with ordinary matter. Billions of dark matter particles might be streaming through a body like Earth at any moment, indifferent to the atoms that make up rocks and oceans. That reality imposes an epistemic humility. The visible universe is a small fraction of what gravitationally matters. Human senses and conventional instruments are attuned to electromagnetic interactions. The universe hides much of its content in channels that are not luminous. This is a conceptual dislocation. The things that govern cosmic history are often those that do not announce themselves through light. How might this invisible majority intersect with deep time narratives about Earth? The direct, dramatic effects are constrained by observations and by the very weakness of interaction. For the overwhelming majority of particle dark matter candidates, the flux through Earth is harmless and essentially undetectable without exquisitely sensitive equipment. Speculative scenarios have been proposed where certain dark matter properties could influence planetary interiors. For example, if dark matter particles were captured and accumulated in planetary cores and annihilated there, they could provide a tiny, long-lived heat source. In principle, such a mechanism could alter rates of geological activity on extreme parameter choices. But current experimental bounds and astrophysical constraints render any substantial heating of Earth by dark matter unlikely. The scientific posture is cautious. Entertain imaginative possibilities, but let empirical limits guide judgment. There are more consequential connections on astronomical scales. Dark matter's role in structure formation affects the timing and environment of star and planet formation. A universe with different dark matter properties will be a universe with a different history of galaxy mergers, different rates of early star formation, and perhaps different abundances of heavy elements, the raw material for rocky worlds and chemistry. Thus, while dark matter is not thought to nudge human history directly from inside a subterranean cavity, it shapes the large-scale roof under which histories unfold. It is the silent choreographer of where and when bright matter can clump and fashion complex chemistry. The experimental chase for dark matter has become a cultural rhythm in physics. Gas meters hum underground. Superconducting magnets breathe liquid helium in cavernous laboratories. Arrays of telescopes scan. For annihilation signals in galactic centers, data pipelines comb through vast images of gravitational lensing for subtle mass distributions. The pattern is iterative. Build a more sensitive instrument, sweep parameter space, refine theory in light of null results, then innovate again. The emotional texture is a mixture of quiet perseverance and dramatic surges of hope when a new anomaly appears. Yet there is also an ethic that has hardened through the years. Extraordinary claims require extraordinary evidence. The community resists premature declarations, knowing that backgrounds, unexpected systematic errors, and statistical quirks can mimic the impossible. The result is an enterprise both disciplined and imaginative. The implications of solving the dark matter puzzle extend beyond physics. Discovering the nature of the dominant mass in the universe would transform narratives about cosmological origins and destiny. If dark matter is a new particle, its properties would inform models of the early universe, of how fluctuations grew into the cosmic web. If, contrarily, gravity requires revision, then the cosmological inferences that rely on a particular theory of gravitation would need re-evaluation. Either outcome would reshuffle the jigsaw that humanity has been assembling. Some pieces would slide into place, others would require recutting. There is an aesthetic lesson here. The fact that most of what holds the cosmic structure together is invisible under ordinary observation forces a philosophical reorientation. The human tendency is to make what is seen the central reference. Modern cosmology teaches otherwise. Structure, persistence, and history can depend on elements that never enter sensory reality but manifest only through their gravitational whisper. This shifts the terms of humility. Knowledge is not simply a matter of enlarging what is visible, but also of inventing methods to sense the shapes that light cannot show. What remains is an open, patient quest. Instruments will grow more sensitive. Theoretical creativity will continue to propose new paths. Cross-disciplinary techniques, from machine learning to novel detector concepts, will search corners of parameter space, once deemed unreachable. Even non-detections are informative. They constrain the designs of models and focus the imagination. In the end, dark matter keeps a certain promise. It is a challenge that reframes human curiosity. It is an invitation to recognize that the visible is a subset of the real, and that comprehension often requires the courage to trust indirect signs. The image lingers, galaxies as beads on a hidden web, a vast scaffolding that does not shine but determines where light can gather. That scaffold is, in its own way, more intimate than the stars. It is the infrastructure of cosmic history. To discover its nature would be to turn a pale, gravitational suggestion into a concrete element of the story humanity tells about the universe and its place within deep time. Until then, the majority of mass remains a patient, silent presence, an unreadable, indispensable part of the jigsaw, urging the hands at the table to keep assembling, to keep listening, and to keep accepting that the most consequential things are sometimes the ones that refuse to be seen. What if the thing that is stretching the cosmos is not a force one can point to on a map, but a mood written into the fabric of space, an emptiness that insists upon becoming larger? That question arrives like a single punctuation mark in the story of everything. The universe is not only expanding, that expansion is accelerating. It is a discovery that readjusts the scales of future history, turning distant galaxies into vanishing islands and reshaping what counts as evidence in the long run. The phenomenon has a name, dark energy, and with that name comes an equally simple, devastating puzzle. Is it a constant of nature, a background hum of vacuum itself, or is it the sign of a dynamic field that will change its tune in the deep future? The evidence is compact and, at first glance, almost domestic. In the late 20th century, astronomers used distant exploding stars, type Ia supernovae, as standard candles. Those burnished beacons, carefully catalogued, told an unsettling tale. They were dimmer than expected, as if the space between galaxies had been stretching faster and faster. The detection was elegant and unsettling in equal measure. It did not require exotic mathematics to read. Light had traveled a longer distance than the simple expanding universe picture predicted. The corollary was inescapable. Some form of repulsive influence was at work on cosmological scales. From that observational hinge, the universe bifurcates into multiple futures, each keyed to the precise character of dark energy. If dark energy is a cosmological constant, Einstein's old tie resurrected in a new context, then empty space carries an energy, density that does not dilute as space expands. Space becomes an inexorable engine of isolation. Distant objects recede beyond observational contact. Entropy winds toward an asymptotic maximum, and the cosmos grows colder and lonelier. If, however, dark energy is the manifestation of a new dynamical field, a quintessence that evolves with time, then the late-time story might be far richer. The field could decay, flip sign, or even grow in strength, each option producing a distinct text of cosmic fate. The distinction seems technical, but its implications are existential. A cosmological constant is a simpler solution, economical, stable, mathematically tidy, yet it carries its own perplexity. Why is its measured value so ridiculously small compared to naive quantum expectations? Quantum fields in empty space seemingly contribute enormous energy densities. Why does the observed vacuum energy sit at a scale that allows galaxies, stars, and observers to exist at all? This is the cosmological constant problem, a mismatch between the expectation from the microscopic rules and the measured grandeur of space. It is less a failure of measurement than a deep tension between the rules that govern the very small and the behavior of the very large. Quintessence and other dynamic field models attempt to soften that tension by promoting vacuum energy to a time-evolving quantity. In such schemes, the slow roll of a field across a potential landscape supplies negative pressure and drives accelerated expansion. The field's velocity and potential determine whether acceleration is mild or explosive, steady or variable. Quintessence is seductive because it permits cosmic histories in which acceleration can begin, end, or reverse. Windows in which galaxies might briefly become islands before regaining contact, or in which expansion slows and allows recontraction. But dynamical models demand their own explanations. What sets the field's initial conditions? Why does it roll so slowly now? Are there couplings to ordinary matter that betray the field's presence locally? For instance, through tiny time variations in fundamental constants, observers respond by pushing measurements to exquisite precision. Cosmology has become a project of statistical tension and cross-checks, supernova luminosities, baryon acoustic oscillations that serve as a standard ruler, the subtle lensing of galaxies by the intervening dark matter, the integrated Sachs-Wolf effect that ties potential decay to the microwave background, and the pattern of temperature anisotropies themselves. Projects such as the Dark Energy Survey, the Euclid mission, the Nancy Grace Roman Space Telescope, and the Rubin Observatory are not merely instruments, they are patient interrogators of a single hypothesis. Each dataset narrows the allowed range for the equation of state parameter W, the ratio of pressure to energy density, and its time dependence. If W equals 1 exactly, a cosmological constant best describes the phenomenon. If W drifts away, the field has been given a surer voice. There is a human cadence to this kind of inquiry. The feeling among observers is a blend of reverence and frustration. Reverence, because the implication that vacuum itself can shape history is a profound twist. Emptiness is not inert. It is an ecological agent of cosmological consequence. Frustration, because models proliferate and many are difficult to probe directly. The work of narrowing possibilities is slow and accumulative. An orchestra of precision instruments gradually resolving a chord into its component notes. Each new survey, each cross-correlation tunes the picture. Null results exert as much force as detections, closing avenues of speculation and concentrating intellectual energy on the paths that remain open. Among the more provocative possibilities is phantom energy, a theoretical regime in which the energy density increases with time. Should W drop below 1 even slightly, repulsion grows stronger as the universe ages and ultimately tears apart bound structures, galaxies, solar systems, planets, in a finite proper time. The Big Rip is cinematic in its logic. The same expansion that once rearranged distances continues into escalation, and the scale factor diverges within the lifespan of the cosmos. It is a dramatic endpoint, and an immediate reminder that subtle differences in a parameter measured today can amplify into radically divergent futures. Detecting the difference between these futures is difficult precisely because the relevant dynamics play out over tens or hundreds of billions of years. Nonetheless, cosmologists are clever. They look for imprints in the growth of structure. How do large-scale fluctuations amplify over time? Does the clustering of galaxies change in a way inconsistent with a simple cosmological constant? They measure the rate at which peculiar velocities decay, the cross-correlations between lensing maps and galaxy distributions, and the time dependence of the distance ladder itself. They listen for deviations in the behavior of gravitational potentials through the integrated Sachs-Wolf effect. Even tiny anomalies repeated across independent datasets could tilt the balance. Parallel to observational efforts are deeper theoretical reflections. Perhaps dark energy is not a traditional field at all, but an emergent phenomenon, a residual of gravitational degrees of freedom that only become apparent on very large scales. Alternative proposals nudge at the foundations. Could modifications of general relativity on cosmological lengths reproduce acceleration without invoking exotic fields? Some modified gravity theories can be tuned to mimic a cosmological constant at background level while producing distinct signatures in growth and lensing. These theories are attractive because they shift the conceptual burden. Instead of inserting new energy into the universe, they reshuffle how mass and curvature relate over great distances. Yet changes to the gravitational law interact heavily with local tests, solar system experiments, binary pulsars, and gravitational wave timings constrain any deviations strongly. The theoretical challenge is to craft a model that produces acceleration without violating the abundant precision tests that have corroborated general relativity at smaller scales. The stakes of getting this right reach beyond forecasting cosmic doom. The identity of dark energy ties into the deepest questions about naturalness, fine-tuning, and the architecture of physical law. If vacuum energy is a constant whose specific value in our universe happens to permit complexity, anthropic reasoning within a multiverse framework becomes difficult to ignore. Perhaps we occupy a bubble with a benign, precisely because only such bubbles permit observers. If, instead, dark energy evolved dynamically and can vary across epochs, The narrative is less fatalistic. History is an open book where physical parameters themselves can be ascribed histories. Either way, the interpretive choices carry philosophical freight about contingency, explanation, and the role of selection effects in science. There is also a quieter, practical implication. Dark energy will, over deep time, determine what remains available as a record. If the universe accelerates forever, the very ability of future intelligences to reconstruct the cosmic past will deteriorate. Redshift will render the cosmic microwave background nearly undetectable. The web of galaxies will fall apart observationally into isolated local systems. The long-term archaeology of the cosmos is time-dependent. The window wherein evidence is plentiful is finite and precious, and that realization imparts an ethical slant to cosmological investigation in the present. Some questions must be answered now, while their traces remain legible. From dark energy, the narrative drifts naturally toward the most intimate engines of gravity, black holes and the singularities they imply. Here, the drama shifts from an expansive loneliness to a compression of everything into a point where known laws surrender their jurisdiction. Black holes are both pragmatic and poetic. They are the endpoints of stellar collapse, the engines of quasar brilliance in the early universe, and, paradoxically, repositories of entropy. They are places where space bends so steeply that causal relationships alter permanently for anything that crosses a boundary, known as the event horizon. Observationally, black holes have left an embarrassment of riches. Gravitational waves have transformed black holes from theoretical curiosities into audible spacetime events. LIGO and its congeners have recorded the inspiral and merger of stellar mass black holes, their waveforms encoding mass, spin, and the nonlinear ballet of general relativity in its strongest regime. The Event Horizon Telescope has, for the first time, photographed the silhouette of a supermassive black hole's shadow, a ring of emission sculpted by the bending of light. These achievements do more than validate equations. They open a new empirical doorway into places where curvature is extreme, and the interface between general relativity and quantum mechanics is most acute. At the heart of a classical black hole sits a singularity, a prediction of general relativity in which density and curvature diverge and the manifold of space-time ends. Singularities are mathematical signposts of breakdown, conditions where the theory no longer offers a predictive framework. They are the cosmic equivalent of a coast where the map lapses. Physically meaningful description demands a quantum theory of gravity, a theory capable of marrying the probabilistic texture of quantum fields with the geometric grammar of space-time. The singularity problem is not merely technical. It is a conceptual fissure that raises uncomfortable questions about determinism, information, and the limits of physical law. Stephen Hawking's insight that black holes are not perfectly black injected thermodynamics and quantum mechanics into the discussion. Hawking radiation implies that black holes have a temperature and entropy, the latter proportional to the area of the event horizon. This black hole thermodynamics reframes singularities as thermodynamic objects and suggests that the maximal entropy of a region is bounded by its surface area, not its volume. From this perspective emerged radical ideas. Information falling into a black hole must, according to quantum mechanics, be preserved. Yet if a black hole evaporates completely via Hawking radiation into a featureless thermal bath, where does the information go? This is the information paradox, a rift between the unitary evolution prized by quantum mechanics and the seemingly irreversible classical black hole. Proposed resolutions are as varied as they are creative. One line asserts that information is encoded subtly in the Hawking radiation itself, correlations that are hard to see but fundamentally present. Another leverages holography, the suggestion that a volume of space can be fully described by degrees of freedom on its boundary, formalized in ATS-CFT duality in specific contexts. Holography hints at a radical economy. The degrees of freedom inside are mirrored by a lower dimensional description without gravity. Other ideas propose that black hole horizons are replaced by quantum fuzzballs, or that Planck scale effects create firewalls that dissolve the smoothness of the horizon. Each avenue attempts to reconcile unitarity with the empirical reality of black holes, but none has yet achieved consensus. Singularities themselves might be smoothed by quantum gravity. Loop quantum gravity suggests that space-time is discrete at the smallest scales, and that classical singularities are replaced by quantum bounces. String theory proposes that classical points are replaced by extended objects, and in certain scenarios, singularities are resolved by stringy physics or by dual descriptions. The empirical problem is acute. Planck scale physics where such resolutions operate, is typically shielded from direct observation by enormous energy scales. Nevertheless, indirect probes exist. Precise measurements of gravitational waves could, in principle, reveal echoes from near-horizon structure. High-resolution imaging of accretion flows can constrain plasma physics against predictions that assume smooth horizons, and patterns in black hole spin distributions bear traces of their growth histories, which touch upon fundamental interactions. Black holes also play a role in deep-time narratives on Earth and beyond. Supermassive black holes anchored in galactic centers shape galaxy evolution through feedback. Jets and winds inject energy into the interstellar medium, regulating star formation and influencing the assembly of heavy elements. In the early universe, black hole seeds, whether from population 3 remnants, direct collapse, or exotic pathways, affect when and how the first luminous objects formed, altering the timeline for chemistry that makes rocky planets possible. Thus, black holes are not only endpoints, they are architects of structure across cosmic eras. The emotional tenor surrounding black holes blends fascination and unease. They are loci where our most successful theories demand amendment, where entropy and information play cosmic games of hide-and-seek, and where observation has finally become precise enough to inform debate. The community is invigorated by the way data has moved from the purely speculative to the directly testable. There is a collective patience as models are proposed and then placed under the severe light of observation. There is also humility. Some questions might be answered only by a revolution in theory, not incremental refinement. Together, the mysteries of dark energy and black holes frame a striking symmetry. One concerns the quiet, large-scale mood of space itself, the propensity of the cosmos to stretch, while the other concerns the violent, small-scale collapses that sever causal contact and demand new quantum language. Both expose the limits of current understanding, and both are increasingly accessible to empirical attack. Dark energy worries about the future legibility of the universe. Black holes worry about the past legibility of processes falling beyond horizons. Both force a reconsideration of what counts as evidence, what is preserved, and what might be fundamentally inaccessible. For those who assemble the cosmic jigsaw, these twin riddles are invitations to a different kind of practice. The work is not merely to graft new pieces onto the existing image, but to refine the very notions of piece and image. Observational ingenuity, theoretical boldness, and philosophical restraint must coexist. Instruments must be built that push precision, theorists must design models that make contact with data, and the public must be offered narratives that carry both wonder and caution. In the interplay between the accelerating fabric of space and the compact enigma of black holes, humanity finds both its smallest certainties and its largest mysteries. The task ahead is centuries long, perhaps longer, to listen, to measure, and to let the faint signatures of the cosmos reframe the story of what it means to know in deep time. What, in the deepest possible sense, is the singularity at the center of a black hole? Is it a cosmic graveyard where information disappears forever, erased from the ledger of the universe? Or is it a doorway, a narrow throat into another region, another universe, a hidden corridor in space-time that conserves pattern under a different bookkeeping? The question arrives like a philosophical razor, precise, inevitable, and capable of cutting through comforting stories. It forces the mind to confront the places where the laws that have served so well simply stop applying. In the classical language of general relativity, a singularity is where curvature diverges, where tidal forces grow without bound, and the manifold of model space-time terminates. It is a line or a point on the map, where the equations say, here, the map ends. The term is mathematical and austere, yet its implications are dramatic. A singularity is not merely a physical object lying somewhere in space, it is a breakdown of description, an index that the theory has reached the edge of its domain. Every trajectory that crosses an event horizon, at least in classical solutions, leads inexorably toward that boundary. Not metaphorically inevitable, mathematically inevitable, that stark conclusion produces a particular emotional register among those who study it. There is awe at the conceptual economy of a theory that can predict such extremes. There is unease at the prospect that determinism might fail at the boundary. There is a stubborn hope that a deeper framework will smooth the edge into continuity. The historical arc of 20th and 21st century physics has been precisely that, facing up to the boundary and inventing new tools to peer beyond. The information paradox sharpens the problem into a dilemma with thermodynamic, quantum, and philosophical teeth. Stephen Hawking's seminal calculation showed that black holes are not utterly black. Quantum field theory on a classical curved background implies particle emission, a thermal spectrum now known as Hawking radiation. If the emission is precisely thermal and featureless, black holes evaporate and vanish into a bath of radiation that carries no imprint of what formed the whole. Quantum mechanics, by contrast, insists that evolution is unitary. Pure states should not devolve into thermal mixtures. The apparent loss of information, the disappearance of a past quantum state into oblivion, threaten to violate the fundamental bookkeeping of quantum theory. The reaction to this threat has been both creative and contentious. Several broad resolutions have been proposed, each with different metaphysical baggage and different implications for what a singularity might physically represent. One class of responses holds that information is preserved and encoded in the Hawking radiation itself. In this view, the thermal calculation is an approximation that fails to capture subtle correlations. If those correlations exist, then the evaporative process is, after a long time, unitary. Information escapes in a scrambled, barely legible form. The page curve, a function describing entanglement entropy over the course of evaporation, should rise and then fall if unitarity holds. Recent theoretical work in quantum gravity, particularly calculations using tools from holography and semi-classical gravity, suggests that such a page curve is indeed possible. These developments use concepts like replica wormholes and gravitational path integrals to show how the entropy of radiation could follow the unitary expectation. The implication, the singularity, need not be a place of erasure. Information is never truly lost, only exquisitely hidden and later revealed in correlations. Another set of ideas treats the black hole interior as physically real but radically different from the classical picture. In string theory, for example, the fuzzball proposal replaces the smooth horizon and singularity with a quantum configuration of strings and branes, microstates that collectively mimic the external black hole fields. There is no interior in the classical sense. Instead, the would-be singularity is a dense, horizon-scale tapestry of structure storing the necessary entropy. Information never crosses an event horizon in the classical way, because the horizon itself is a macroscopic manifestation of microstructure. Philosophically, fuzzballs preserve unitarity by denying the classical interior. Loop quantum gravity and related approaches take another tack. Quantum discreteness of space-time may prevent singularities from forming. In these schemes, what classical equations predict as infinite curvature is tamed by quantum effects, leading to a bounce or a transition. The Planck star idea is evocative. A collapsing core reaches Planck-scale densities and then undergoes a quantum rebound, releasing stored information over long time scales. Such scenarios soften the finality of singularities and offer a route by which information might be preserved in a form that eventually leaks out. Yet other speculative proposals take the singularity at face value while relocating the conservation of information in unexpected places. The idea of baby universes, causally disconnected regions spawned by topological change, envisions information flowing into newly created domains beyond the observational reach of the parent universe. From the perspective of the parent cosmos, information would be irretrievably lost. From a multiverse perspective, it would be conserved in a larger bookkeeping that includes the descendants. This move relieves the paradox by appealing to a bigger ledger, but it trades empirical closure for ontological expansion. The conservation law is saved by postulating inaccessible sectors. The holographic principle offers another radical reconfiguration. It suggests that the degrees of freedom of a region of space can be encoded on its boundary, an economy of description in which volume is secondary to surface. Concrete realizations of holography, such as AD-CFT duality, show how gravitational dynamics in a bulk spacetime can be exactly equivalent to a quantum field theory without gravity on a lower dimensional boundary. If this equivalence holds in physically relevant settings, then the black hole interior and its singularity are dual to unitary dynamics in a non-gravitational theory. Information is never lost, because the dual description is manifestly unitary. The catch is that our real universe is not asymptotically anti de Sitter, and translating the remarkable mathematical control of AD-CFT into cosmologically realistic contexts is an ongoing challenge. Nevertheless, holography has reshaped thinking. Perhaps the singularity is not a fundamental erasure, but a region whose information is faithfully represented elsewhere. Intertwined with these conceptual proposals are bold conjectures that connect entanglement and geometry. The ER-EPR conjecture, the suggestion that Einstein-Rosen bridges wormholes are equivalent to entangled quantum pairs, hints that entanglement is the fabric of space-time itself. If entanglement creates geometric connectivity, then the pattern of quantum correlations across a horizon might be reinterpreted as a subtle wormhole structure connecting the radiation to the interior. This idea is provocative because it reframes what a horizon is, not a strict causal severing, but a boundary threaded by non-trivial quantum geometries. However speculative, ER-EPR gestures toward a unifying intuition, information, and geometry are two faces of a deeper relation. These theoretical vistas are intellectually rich, but they face the blunt arbiter of observation. Can empirical data distinguish between these competing pictures? Here, gravitational waves enter the story as a new, potent messenger, the title and promise of the next chapter. 7. Gravitational waves in space-time. Gravitational waves were predicted a century ago by the mathematical structure of general relativity. Their detection in the 21st century represents one of the most profound confirmations that space-time is not an inert stage, but a dynamical medium. LIGO's first detection in 2015, a signal of two stellar mass black holes spiraling and merging, was not merely an experimental triumph. It opened an audio-like channel with which the cosmos speaks. For the first time, humanity could literally listen to the strong field gravity where horizons form and space-time is violently distorted. The emotional and epistemic consequence of gravitational wave astronomy is immediate and subtle. The detection validated the basic picture. Black holes exist, they merge, and their mergers radiate energy in the form of ripples that traverse the universe. The observed waveforms matched numerical relativity's predictions with breathtaking fidelity. That agreement reinforced the robustness of general relativity in regimes where curvature is intense, yet the very success of the classical theory is also a reminder. Gravitational waves so far have confirmed the theory where it applies. They have not yet exposed where it fails. That caveat is important. Gravitational waves probe the external dynamics of merging objects, the approach, in spiral, merger, and ring down. The ring down phase, the dying vibrations of the newly formed black hole, encodes the quasi-normal modes determined by mass, spin, and the structure of the horizon. Measuring these modes tests the no-hair theorems. Are black holes wholly described by a small set of macroscopic parameters? Deviations from expected mode spectra would hint at new physics, modifications of gravity, presence of matter around the horizon, or exotic horizon structure. In this sense, gravitational waves are a scalpel, not a microscope. They reveal the external face with precision, but do not, at first glance, pry open the inner sanctum behind the event horizon. Still, creative theorists have shown that gravitational wave signals might harbor signatures of quantum modifications near horizons. The proposed echoes in post-merger signals are one class of such signatures. If the horizon is replaced by a partially reflective surface at near Planckian scales, a fraction of the wave packet could reverberate between that surface and the light ring, producing delayed, diminished pulses, echoes. Searches for echoes in LIGO data have produced tantalizing hints and contested null results. The statistical difficulty is severe. Echoes would be weak and their morphology uncertain. But gravitational wave data continues to accumulate. Detectors grow more sensitive, and the statistical power to search for subtle post-merger structure increases. Beyond echoes, gravitational wave observations offer tests of the strong field dynamics and the propagation of gravity across cosmological distances. Measuring the speed of gravitational waves during the binary neutron star merger GW170817 constrained deviations from general relativity that had been proposed to explain cosmic acceleration. Many modified gravity models were sharply disfavored. Such constraints show the reciprocal authority of gravitational wave data. They can protect or prune entire classes of theoretical ideas. Yet gravitational waves have other promises that reach deeper into cosmological memory. The stochastic background of gravitational waves, a faint, diffuse hum permeating the universe, could be a fossil of processes in the early cosmos. Inflationary models predict a primordial gravitational wave background whose amplitude and spectral shape would encode the energy, scale, and dynamics of the earliest expansion. Detecting primordial gravitational waves in the millihertz to nanohertz bands, the regime that future detectors like LISA and pulsar timing arrays will probe, would be an extraordinary window into epochs otherwise inaccessible. Such a detection would not resolve a black hole singularity, but it could constrain models of the universe's birth, informing whether an inflationary smoothing occurred and to what energy scale. It would, indirectly, sharpen the constraints on any prehistory by revealing the imprint of processes that occurred when classical notions of space-time were already well defined. The detection of gravitational waves has therefore transformed philosophical questions into empirical programs. The question of whether a black hole's singularity consumes information outright or whether information escapes in some encoded form is now connected to what can be measured in the in-spiral, merger, and ring-down. If the no-hair theorem holds exactly, then classical merger waveforms are determined by a small set of parameters. If violation appears, then new degrees of freedom, perhaps tied to the microstructure that stores information, may be implicated. There are practical limitations, too. Gravitational waves cannot extract information from behind an event horizon in the classical sense. Signals originating inside the horizon are causally disconnected from the outside. Any information that appears in an external signal must be connected to the horizon scale or exterior dynamics. Thus, gravitational waves will not directly reveal the fate of information that falls into a classical singularity. Their power is to test whether the exterior behaves in ways consistent with classical horizons or whether subtle horizon scale modifications transmit signatures outward. Future instruments will expand both the frequency and sensitivity ranges. Space-based detectors like LISA will listen to lower frequency bands, targeting massive black hole mergers and extreme mass ratio and spirals that probe motion deep in the potential wells near supermassive objects. Pulsar timing arrays will hunt for nanohertz waves from the slow dance of the largest black hole binaries, and third-generation ground-based detectors will push to higher sensitivity, broadening the horizon of accessible events. Each improvement increases the odds of catching the tiny departures from classical expectations that might betray quantum gravity's imprint. Beyond detectors, theoretical advances in quantum gravity, in holography, and in semi-classical methods have started to produce testable predictions. Recent calculations using semi-classical gravity reproduce page curves under certain assumptions, and holographic models map black hole evaporation onto unitary boundary dynamics. These are not yet definitive answers. They are promising map fragments that must be checked for consistency with observation and extended beyond idealized settings. Here again, the work is iterative. Theory suggests signatures, instruments look for them, and data either elevates or constrains the proposals. The current balance of evidence is soberingly precise and provocatively incomplete. General relativity, boasted by gravitational wave detections, remains extraordinarily successful in the macroscopic regime. Quantum theory demands that information not vanish. Reconciling the two has produced ideas of remarkable subtlety, information encoded in correlations, horizons laced with microstructure, emergent time, holographic encodings, baby universes, and Planckian bounces. Gravitational waves provide a new language to test facets of these ideas. Yet they are not a panacea. The deepest processes likely play out at Planckian scales shielded from direct view by causal structure. That acknowledgement carries an emotional tone, both elegiac and invigorating. It is elegiac because some answers may remain permanently out of reach for observers confined to a single causal patch. It is invigorating because the tools now available, both theoretical and observational, allow a disciplined, empirical assault on what once seemed purely metaphysical. The paradox is that proximity to the problem has grown while its core remains veiled. Humanity has never been closer to the strong gravity regime experimentally, and simultaneously the puzzle demands conceptual revolutions. In the end, the singularity question and the story of gravitational waves fold into a single lesson about the nature of inquiry. In deep time and extreme conditions, where classical equations break, new frameworks must be invented. Where observation is limited by horizons, creative indirect tests must be devised. Where paradoxes arise, humility and methodological rigor are the proper responses. The possibility that information is preserved, whether in subtle correlations in Hawking radiation, in holographic encodings on horizons, or in safe vaults of baby universes, keeps the investigators building instruments, writing calculations, and listening to the cosmos with patient hope. The narrative remains open. Gravitational waves have been detected, but they have revealed only the first chords of a far larger symphony. The next movements will be written by sharper instruments, by theoretical bridges across quantum and gravitational thought, and by the patient accumulation of evidence. Whether the singularity is a final erasure or a gateway depends on physics yet to be discovered. What is certain is that the Endeavor to know will continue with the same mixture of awe and restraint that has animated the search from the beginning. What does it mean for time to have a direction? The question arrives not as a mere curiosity about clocks and calendars, but as a profound fissure in the way reality narrates itself. It is the asymmetry at the heart of every memory, every fossil, every record. Causes precede effects. Ice melts but does not spontaneously reform. Chemical gradients are consumed rather than created. This persistent orientation, the arrow of time, is the invisible scaffolding that permits history to accumulate. Yet the fundamental equations that govern particles and fields are, for the most part, time-symmetric. The tension between reversible microscopic laws and an unmistakable macroscopic arrow is one of the deepest puzzles in physics. And in the account of deep time, the paradox begins with a stubborn fact of experience and ends in a labyrinth of conceptual proposals. On laboratory benches and in planetary geology, processes are irreversible. Glasses shatter into fragments. Rivers carve canyons and do not reconstruct mountains by undirected flow. Thermodynamics codified this regularity in its second law for isolated systems: entropy, a quantitative measure of microscopic disorder, or more carefully, of missing information about microscopic states, tends to increase. Yet the microscopic dynamics that underlie thermodynamics, classical or quantum, are reversible in principle. If one could reverse all velocities in a Newtonian gas, it would retrace its steps. Ludwig Boltzmann confronted this tension by interpreting entropy statistically. Low entropy states are rare. The second law is a statement about overwhelming probability, not absolute prohibition. The arrow of time, in Boltzmann's picture, is a statistical fact of ensemble weighting. Even an account as elegant as Boltzmann's bumps into hard questions. Why, if entropy increases toward the future, was it so low in the past? The statistical account transforms the problem into a boundary condition problem. To explain the directionality seen today, one must assume a special low entropy beginning. This idea, variously called the past hypothesis, is simple in its statement and stubborn in its implications. The universe began in an extraordinarily special configuration, atypical among the myriad microstates compatible with its macroscopic parameters. The immediate question is then not merely physical but almost theological in flavor. Why this initial specialness? Why not a past already filled with thermal equilibrium, devoid of history and structure? The puzzle becomes sharper when gravity enters the stage. In ordinary non-gravitational systems, spatial uniformity corresponds to high entropy. A gas spread evenly across a box is more probable than one clumped into a corner. Gravity inverts that intuition. A homogeneous cloud of matter is, in a gravitational universe, a fairly low entropy configuration because gravity prefers clumping. Over time, slight perturbations grow, matter collapses into stars and black holes, and the entropy associated with gravitational degrees of freedom increases enormously. The uniform high-temperature plasma of the early universe, perfectly smooth on large scales, was thus a low-entropy gravitational state. The arrow of time in cosmology is deeply entangled with this gravitational asymmetry. The early universe's smoothness is the secret seed of subsequent structure and of the very possibility of records and memory. Roger Penrose captured this insight with a stark phrase: "The low gravitational entropy of the Big Bang is encoded in the smallness of the Weyl curvature." In his account, the initial conditions suppressed the degrees of freedom associated with tidal distortions and gravitational radiation. Black holes, with their enormous entropy, were absent. The eventual production of black holes, the universe's entropy reservoirs, is what drives entropy growth. Penrose's view reframes the past hypothesis as a gravitational selection. The cosmos was not randomly chosen, but begins in a very special geometric state. Why that state? Penrose offered no simple dynamical mechanism. The condition remains an empirical input, an extraordinary boundary datum that physics must reckon with. Inflation complicates and clarifies matters simultaneously. The inflationary picture, a rapid stretching of space that smooths and flattens the cosmos, accounts for the observed homogeneity and the specific spectrum of primordial fluctuations. Yet inflation itself seems to presuppose a low entropy patch to begin. The exponential stretching tends to erase pre-existing irregularities, making many prior histories observationally irrelevant. But the act of producing a region ready to inflate may be rare in the space of possible microstates. In other words, inflation may explain how a smooth, low-entropy-looking patch produces the observed universe, but it does not fully answer why such a patch existed in the first place. The problem recurs. Some specialness has to be posited. Or else one appeals to global multiverse scenarios where pockets like ours arise among an enormous ensemble. Statistical mechanics offers operational pathways past sheer proclamation. Modern fluctuation theorems, Jarzynski, Crookes, and related results refine the second law into precise statements about the probability of entropy decreasing fluctuations in small systems or over short timescales. Those theorems are remarkable because they are experimentally testable and because they make precise how irreversible-looking behavior emerges from reversible laws once coarse graining and finite sampling are introduced. In microscopic systems, entropy can transiently decrease. In macroscopic realms, it almost never does. These laboratory verifications of fluctuation relations are not philosophical panaceas, but they demonstrate that irreversibility is a statistical emergent property, not an inviolable metaphysical decree. Quantum mechanics adds layers of nuance. Quantum unitary evolution is time reversible, yet the measurement process, with its collapse or decoherence, seems to introduce an arrow. Decoherence theory explains the apparent collapse as the irreversible entanglement of a system with an environment, rendering phase relationships inaccessible to local observers. The arrow of decoherence aligns with the thermodynamic arrow. Once information about relative phases is dispersed into many degrees of freedom, reconstruction becomes practically impossible. Still, the foundations are debated. If the universe evolves unitarily, then the global quantum state retains information, and irreversibility is again a matter of coarse graining and subjective access. If quantum gravity renders time emergent, if temporal progression is not a fundamental parameter but appears only in specific, semi-classical regimes, then the arrow of time itself may be a metastable emergent property tied to particular states of entanglement. This suggestion that time emerges from quantum entanglement is one of the most evocative ideas to arise from recent theoretical work. Holographic principles and thought experiments in ADS-CCFT hint that geometry and connectivity of space-time may be encoded in patterns of entanglement across underlying degrees of freedom. If spatial geometry can be reconstructed from entanglement, perhaps temporal progression and its orientation can be similarly read from how entanglement grows or is redistributed. The growth of entanglement in a system, particularly following an out-of-equilibrium disturbance, has a definite direction. In many-body quantum systems, entanglement spreads outward from local disturbances in a way that resembles causal propagation. Could the cosmological arrow then be a manifestation of global entanglement dynamics that begins in a special low entanglement initial state and evolves toward higher entanglement? The idea connects with a thermodynamic viewpoint but relocates the primary quantity from coarse-grained entropy to patterns of quantum correlation. The role of black holes intensifies these questions. Black holes are thermodynamic heavyweights. Their entropy, proportional to horizon area, dwarfs the entropy of ordinary matter. The formation and evaporation of black holes complicate any naive picture of entropy bookkeeping. If a universe produces many black holes, entropy rises dramatically. Yet subtle questions remain about information flow. If black holes evaporate and release Hawking radiation, is the outgoing radiation precisely thermal, or does it encode correlations that preserve unitarity? Recent theoretical progress suggests mechanisms by which entropy of radiation follows a page curve compatible with unitarity, implying that information becomes encoded in subtle, non-local correlations. If so, then the arrow of time is compatible with unitary quantum evolution. But its macroscopic irreversibility remains a product of coarse graining and access. The tension between global reversibility and local irreversibility echoes in cosmological thought experiments. Boltzmann himself flirted with a radical proposal. Perhaps the universe is eternal in time and, given infinite durations, rare fluctuations could produce low-entropy pockets like our present environment. Such pockets could temporarily support structure and observers. The proposal creates an uncomfortable implication. It is far more likely that a tiny fluctuation produces a solitary conscious brain, a Boltzmann brain, complete with illusory memories, than that a gigantic coherent universe like ours fluctuates into being. Because we observe a rich, coherent cosmos with consistent records, Boltzmann's fluctuation scenario seems empirically implausible. Avoiding Boltzmann brains pushes cosmological models toward genuine, low-entropy initial conditions rather than random fluctuations. It is another pressure in favor of the past hypothesis or similar selection criteria. Cosmological expansion may also act as a facilitator of the arrow. As the universe expands, it provides the thermodynamic gradients necessary for local entropy production. Stars form and burn fuel, generating the flows that permit life and the creation of durable records. A static or contracting universe would limit such opportunities. In this pragmatic sense, the cosmological arrow, the direction of expansion set by the Big Bang, and the thermodynamic arrow are allies. Expansion sets the stage for gradients. Gradients enable irreversible processes. Irreversibility enables records and history. Yet the cosmological arrow does not reduce the problem, it reframes it. One still must explain why expansion began in a low entropy state rather than being a temporal mirror image. A rich body of contemporary thought explores whether the arrow can be derived from within a deeper microphysical theory, rather than imposed as initial data. Proposals range from invoking specific quantum gravitational boundary conditions to adopting a view in which time's arrow is a perspectival phenomenon tied to the division of systems into subsystems and environments. Cardinal Rovelli and others have formulated a thermal time hypothesis. In generally covariant systems where no external time parameter exists, a notion of time can be recovered from the statistical state of the system itself. In that framework, the arrow of time is not fundamental, but relative to the chosen macro state. Different observers or partitions may experience different thermodynamic flows. While conceptually elegant, translating such ideas into cosmologically testable predictions remains a challenge. Philosophical humility is demanded by these deep questions. The arrow of time sits at the intersection of empirical measurement, statistical inference, and metaphysical assumption. It is tightly connected to the very possibility of historical knowledge. Without an arrow, there could be no accumulation of records, no fossils, no archaeology. The asymmetry is therefore not just a scientific curiosity, it is the condition of intelligibility. For the narratives that reconstruct deep time, that interdependence reappears across scales, geological stratigraphy, chemical disequilibria in rocks, cosmic microwave background, anisotropies. All are records that exist because physical processes generate durable markers of their passage in a way that is not symmetric under time reversal. The human implications are intimate. The past hypothesis and related ideas make an empirical demand that, at first glance, appears anthropocentric, but the demand is less about human significance than about the necessary structure for observers to exist and to remember. Life, cognition, and cultural continuity exploit thermodynamic gradients and irreversible chemical cycles. These, in turn, rely on a cosmological history that has been shaped by a very specific entropic trajectory. The realization is sobering and, in its way, consoling. The asymmetry that enables curiosity is part of the same cosmic story that permits planets, molecules, and memory. What, then, of the possibility that time itself is not fundamental? If space-time emerges from deeper degrees of freedom, then the arrow might be an emergent, contingent feature of particular emergent regimes. In such a view, there may be meta-histories in which different arrows coexist or where the arrow flips across a bounce or phase transition. These scenarios are speculative but not vacuous. They reshuffle questions and invite new observational strategies. Look for relics of pre-semi-classical epochs in primordial gravitational waves. Search for constraints on models that could permit time reversal across cosmological bounces. Refine our statistical understanding of initial conditions and theories that supply their own measure and configuration space. Experimentally, the route forward is as much conceptual as instrumental. Laboratory tests of fluctuation theorems and non-equilibrium quantum dynamics tighten understanding at small scales. Cosmological probes refine our picture of the early universe's geometry, its homogeneity, and the statistical properties of primordial fluctuations. Progress in quantum gravity and holography sharpens the catalogue of possible initial conditions and the mathematical vocabulary for discussing emergence. Across these domains, the pattern is familiar, an interplay of theory, observation, and philosophical clarity. Each refinement narrows the space of plausible origins for the arrow, even if full resolution remains distant. The mystery of time's arrow has a moral rhythm that echoes the earlier theme of preservation versus erasure. Just as geological and cosmological processes can erase traces of past civilizations, the arrow itself determines what can be recorded and what can be lost. Irreversibility is both the condition for reliable records and the engine that consumes the gradients those records exploit. The narrative of deep time, therefore, depends on the double-edged quality of entropy. It permits history by making certain transitions effectively one way, and it obliterates histories by driving systems toward equilibrium. In the end, the question of why time as a direction is not merely a technical conundrum at the edge of physics, it is a foundational inquiry into how the universe comes to sustain narratives at all. The current consensus that the arrow arises from special low-entropy initial conditions amplified and shaped by gravity, quantum mechanics, and cosmological expansion is a provisional synthesis that honors empirical constraints while admitting deep conceptual gaps. Whether those gaps will be closed by a new dynamical explanation, an emergent account from quantum entanglement, or by an acceptance of a fundamental boundary condition remains open. What endures is a posture, curiosity edged with modesty. The arrow of time is at once the background hum of all human history and a profound, unresolved question about the universe's most basic architecture. To confront it is to confront why stories can be told at all, why rocks can be read, why starlight can be interpreted, why memory and record are possible. The inquiry ties together the micro and the cosmic, the laboratory and the sky, and it returns the narrator to the core lesson of deep time, that knowledge advances by assembling fragments, recognizing the limits of preservation, and accepting that some answers will demand revolutions in thought. The arrow points onward, the work of understanding follows it, patient and relentless. Why does time seem to flow only one way? The question arrives as a tension between two truths that do not want to be reconciled easily. The microscopic laws of physics are largely indifferent to the direction of time, or the macroscopic world, memories, fossils, the arrow of history, insist on asymmetry. That insistence is not a quirk of human psychology. It is the scaffolding of all narratives, the thermodynamic backbone of cause and effect. Yet it sits atop equations that, at their core, play equally well forward and backward. The paradox is not merely technical, it is existential. It asks how a universe governed by reversible microdynamics produces irreversible histories. And it asks whether the sense of past and future might be different, perhaps even reversed, in parts of reality yet unseen. On the simplest level, the origin of time's apparent one-way flow is statistical. A handful of atoms obey Newton's or Schrödinger's equations that do not prefer a forward motion. A soup of many particles, however, behaves differently. Entropy, the quantitative expression of missing information about microscopic states, tends to increase. The second law of thermodynamics is nothing mystical. It is the statement that, for systems with an enormous number of microstates, configurations with higher entropy vastly outnumber those with lower entropy. A spilled cup of coffee will not spontaneously reassemble because the ordered state it once occupied is astronomically less likely than the disordered alternatives. The familiar asymmetry emerges as probability and counting. But the statistical account leaves a deeper demand. If entropy tends to grow toward the future, why was entropy so low in the past? Why did the universe start in a configuration so special that irreversible phenomena could subsequently unfold? This is not an idle philosophical aside. It is the hinge on which the whole story of records, fossils, and human knowledge swings. Without extraordinarily low entropy initial conditions, there would be no gradients to drive stars, no chemistry to make planets, no durable changes to be read like pages in a book. The past hypothesis, the empirical proposition that the universe began in an unusual low entropy state, has thus become central. Yet it is not explanatory. It is boundary data. Why those particular boundary conditions? That remains the deep conundrum. From the vantage of cosmology, gravity complicates the picture in an illuminating way. Where non-gravitational intuition equates uniformity with maximum entropy, gravity inverts the expectation. A smooth cloud of matter is a low-entropy gravitational state because gravity's appetite is for clumpiness. Over time, small irregularities grow into stars, galaxies, and black holes, the latter repositories of enormous entropy proportional to horizon area. The Big Bang's early smoothness is therefore the seabed of a directional thermodynamic unfolding. A universe that began oddly ordered in its geometry could naturally produce the relentless production of entropy that defines what is experienced as the future. Yet many theorists embrace the unsettling possibility that what counts as past and future might not be universal. In speculative cosmological frameworks, the arrow of time could be a local, emergent property rather than a global, cosmic mandate. Imagine, for a moment, a larger space-time that contains two regions in which entropy increases in opposite directions. Each region's inhabitants would experience a forward arrow aligned with their own local entropy growth. Neither would find time reversed relative to themselves. From the outside, this sounds paradoxical, but internally it is coherent. The sense of forward is tied to the direction in which records accumulate and in which causally admissible processes leave durable imprints. Physicists have explored several models that toy with this notion. Some proposals sketch a time-symmetric universe in which a low entropy, Janus point in the middle, gives rise to two thermodynamic arrows pointing opposite ways away from that point. In such visions, the universe as a whole has no preferred time direction. Rather, the arrow is a feature that emerges within each wing. Other approaches use CPT symmetry, the combined reversal of charge, parity, and time, to imagine a cosmos in which an antimatter-dominated region is, by a certain symmetry, a time-reversed mirror of ours. Those ideas are mathematically seductive because they trade an inexplicable initial condition for symmetry structures that are already part of the quantum field theory toolkit. Important caveats follow. A reversed arrow is not simply writing history backwards. An observer in a region where entropy increases in the opposite direction would still experience causation, memory, and thermodynamic gradients in a way indistinguishable from ours. Records would be laid down toward their own future. The deeper difficulty is whether different arrows can coexist and interact. If they did, what would the interface look like? The intuitive answer is forbidding. To cross from one arrow to another is to encounter a boundary where conventional causality unravels. From a practical point of view, interactions across such a boundary would be extraordinarily suppressed or impossible. Otherwise, the macroscopic contradictions, violations of energy conditions, runaway entropy flows would become evident. In effect, arrows pointing in opposite directions would be insulated from one another. The result is an image of many causal islands, each with its own thermodynamic narrative, adrift within a larger structure that resists simple observation. For curious minds, the image is both tantalizing and humbling. The cosmos could contain regions where before and after are locally inverted, and yet those regions would be forever remote in the sense that their reversedness leaves no accessible footprints on our side. The speculative terrain is narrow where observation matters. Present-day empirical science is constrained by horizons and by the smoothing effects of inflation. If our universe underwent an early inflationary phase, it would have stretched and erased many plausible traces of a pre-inflationary era. Just as sanded tree rings obscure the details of a storm long ago, cosmological smoothing blurs the imprint of whatever preceded the hot Big Bang. The upshot is that reversed arrows and other cosmic domains may be theories that are internally consistent and even beautiful, but remain stubbornly resistant to direct test. And yet the ambiguity invites thought experiments with real bite. If the arrow is a contingent outcome of initial conditions or of entanglement structure, then addressing its origin demands more than clever mathematics. It demands new empirical strategies, creative observables, or a conceptual breakthrough that shows how a symmetric microphysics yields asymmetric, macroscopic histories without appealing to brute boundary conditions. If questions about time's direction require rethinking the architecture of causation, the search for life beyond Earth calls for the same humility about hidden records. Both inquiries are, at heart, exercises in reading incomplete archives. One asks whether entropy, records, and causation are local accidents or universal laws. The other asks whether life, the chemical and organizational processes that produce observable biomarkers and technological signatures, is a rare flourish or a commonplace reaction in the universe's vast laboratory. Both are constrained by preservation bias. Processes that erase evidence leave no witnesses, and what remains is a sliver sifted by contingencies of chemistry, geology, and cosmology. In that light, the small famous anomaly detected in 1977, the signal indelibly labeled "Wow!" becomes more than a footnote. It is a concentrated lesson about expectation, method, and the fragility of evidence. The experiment that recorded the pulse was a radio survey of the sky near the hydrogen line at 1420 MHz. For 72 seconds, a narrowband burst appeared in the data, strong, localized, and not obviously terrestrial. The printout produced an involuntary "wow" of astonishment from the astronomer who first examined it. Then the normal scientific rhythms resumed. Attempts to repeat the signal failed. Other instruments saw nothing. Many plausible terrestrial and astronomical explanations were considered and then set aside or found wanting. Over decades, the "wow" signal has assumed a symbolic role in the SETI story, emblematic of how slender a thread connects evidence to inference and how easily one's hopes can be caught on a transient, unrepeatable flicker. The search for extraterrestrial life has diversified enormously since that single event. One branch seeks biosignatures, chemical disequilibria in planetary atmospheres that betray biological processes. Oxygen paired with methane, for example, is a disequilibrium that on Earth is maintained by biology. Telescopes such as the James Webb Space Telescope and ground-based spectrographs are searching in painstaking campaigns for the faint spectral fingerprints of molecules in exoplanet atmospheres. Another branch, SETI, in the broad sense, searches for techno-signatures, deliberate beacons, narrowband radio transmissions, pulsed lasers, or waste heat on astronomical scales. Each strategy is tuned to different assumptions about what alien life would prioritize: communication or survival, loudness or stealth. The detectability of such signatures is a function of both distance and time. An intentional radio beacon must be powerful, tightly beamed, or sustained for an enormous interval to cross interstellar gulfs and still be discernible. A civilization that briefly broadcasts for a few centuries in a galaxy that has been in place for billions of years may leave no one to hear unless timing aligns. That is the temporal aspect of the Fermi question. Even if life is not exceedingly rare, the overlap of communicative windows can be vanishingly small. The Drake equation formalizes the uncertainty, but it also hides the asymmetry. The question of how long matters as much as how many. Then there are techno-signatures that do not require purposeful transmission. Megastructures, hypothetical constructs such as Dyson spheres that encapsulate a star to harvest energy, would produce telltale anomalies in the infrared spectrum of their host stars. Unexplained infrared excesses and irregular light curves attract attention precisely because they are difficult to produce by known natural processes. Yet natural astrophysical phenomena often confound the search. Dust, variable accretion, and stellar activity can mimic or mask the signatures under scrutiny. The wow signal teaches patience about anomalies and rigor about dismissal. Equally important is the idea of interstellar archaeology, the search for artifacts rather than broadcasts. Probes left in stable orbits, on the moon, or embedded in near-Earth asteroids would be cultural fossils that persist far longer than atmospheric or radio emissions. The preservation of such artifacts depends on environmental stability. The moon's quiescent environment preserves impact scars and human-made debris for millions of years. On Earth, tectonics and erosion rewrite the surface in ways that make long-term survival unlikely. That very fragility reiterates the earlier lesson. Evidence for past intelligence is ephemeral in many environments, but durable in certain niches. If civilizations elsewhere seeded probes across the galaxy, we might expect to find them in places where preservation is facile, the equivalent of cosmic dry caves. But the absence of known probes raises as many hypotheses as it does frustrations. Probes could be rare. Not sent, they might deliberately avoid detection, or perhaps the cost-benefit calculus for truly long-lived artifacts differs. From simple models of expansion, the concept of messengers spans a spectrum. Electromagnetic pulses, robotic emissaries, and passive megastructures all occupy different niches of detectability and longevity. A beacon aimed at interstellar neighbors can announce presence quickly, but requires energy and intent. A probe that seeds itself and replicates, the von Neumann idea, promises persistent presence but raises ethical and practical questions. Is replication desirable for advanced intelligences? Might self-reproducing probes have perished, mutated, or become invisible in ways that confound detection? The silence implies constraints, but not a single conclusion. These practical concerns circle back to deep time themes. If civilizations arise and fall on timescales small compared to geological processes, their evidence will be truncated or erased. A flourishing technological species might see its artifacts reduced to geochemical anomalies, scattered debris, or traces of metals reworked into new geological fabrics. The archival record available to a future archaeologist, whether human or alien, depends critically on the interplay between durability and transformation. Just as tectonic burial can erase entire cities, cosmic and planetary processes can erase entire technological epochs. Thus, the argument that we have not detected extraterrestrial civilizations is less conclusive than it first appears. Absence of evidence is not evidence of absence. It is evidence of the difficulty of preservation and detection across the scales of space and time. There are also philosophical turns in the search for life that mirror the worries about time's arrow. If time's direction is a local emergent property, the search for life might be an equally local enterprise. Life might flourish in thermodynamic niches and die where gradients disappear. The persistence of biosignatures across cosmological epochs depends on the same entropic flows that give direction to time. In that sense, the question of whether time could flow backward somewhere and whether life could exist, there are not entirely separate philosophical curiosities. Both probe how order emerges, persists, and is recorded in systems driven by energy fluxes. The practical demand of these reflections is modest but urgent. Build instruments with patience, diversify the modes of searching, and cultivate an epistemic humility that respects the fragility of record. Radio arrays must be paired with spectroscopic surveys, infrared inventories, and targeted archaeological searches within the solar system. Data must be shared, anomalies must be replicated or refuted, and tentative signals must be treated with both wonder and methodical skepticism. The wow signal is a lesson in restraint. For a moment, it illuminated the possibility of contact and then receded, leaving a residue of organized curiosity. Ultimately, the two threads run parallel. The study of time's direction and the search for life are both efforts to read a history that has been heavily edited by natural processes. The arrow of time tells the conditions that allow records to exist at all. The hunt for life depends upon those records being durable enough to be read. Both quests confront limits, observational horizons, smoothing processes, entropic erasure, and the rarity of overlapping windows. Both demand a blend of theoretical daring and empirical patience. There is a human cadence to that blend. Scientists will continue to push instruments and methods, to refine models of cosmology, and to search for signals with an ever more systematic curiosity. The work is slow because the universe is indifferent, and because the best answers come from patient accumulation of constraints, rather than sudden revelations. Yet the culture of investigation is sustained by the same mixture of humility and hope that animates any long-term inquiry, the willingness to follow slender traces, to accept null results as information, and to be surprised when the cosmos finally chooses to speak. The result is an intellectual posture well suited to deep time, a readiness to ask big questions, to live with provisional answers, and to cherish the fleeting moments when the universe offers a clear, replicable whisper rather than a lonely, unrepeatable wow. Part 9. The silence, Fermi's question, the great filters and the hidden landscapes of reality. What does it mean? In a universe so vast and old that the night remains stubbornly quiet? The question is simple, almost rude in its economy. If life and intelligence are natural outcomes of chemistry and time, then where are the others? Enrico Fermi's casual, famous question, where is everybody, sits at the hub of this unease. It is both a pragmatic problem in observational astronomy and a philosophical prod. The absence of a clear signal becomes itself a data point, a stubborn piece of the cosmic puzzle that demands explanation. The Fermi paradox is not a single argument, but a library of tensions. On the one hand is the scale argument, billions of galaxies, each with hundreds of billions of stars, many of them older than the sun, many encircled by planets. Simple probabilistic thinking suggests that even with conservative assumptions, some fraction of those planets should have produced life, and some fraction of that life should, in time, have produced technology. On the other hand is the empirical fact. Humanity has no confirmed, repeatable evidence of extraterrestrial intelligence. No unambiguous radio beacon has been catalogued, no megastructure has been confirmed, no probe has arrived with undeniable provenance. That mismatch sharpens into hypotheses, speculations, and disciplines of inference. Either life or technological civilizations are exceedingly rare, or our ability to detect them is limited in ways we underestimate. Or there exists a selection effect that biases our viewpoint. The first family of explanations is the rare earth line. The chemistry of life and the evolutionary path to intelligence may be so contingent that even with billions of planets, very few traverse all the necessary conditions: planetary stability, a benign star, a magnetic field to shield radiation, plate tectonics to cycle nutrients, a long period without sterilizing impacts, and a particular sequence of contingency events, the emergence of eukaryotes, the invention of multicellularity, a long evolutionary corridor to technological cognition, could combine to make intelligence. An extreme outlier. Viewed this way, humanity's existence is a slender conjunction of fortunate circumstances. The silence is unremarkable because the cosmos simply did not produce replicates. A second family places the obstacle, not at origins but along the timeline, the great filter. This idea reframes the paradox as a bottleneck in the trajectory from inanimate chemistry to galaxy-spanning civilization. The filter could lie in the past. The hard step might be the origin of life or the origin of intelligence, which would make our presence unusually fortuitous. Or the filter could lie ahead. Civilizations might routinely self-destruct, exhaust their resources, collide catastrophically with their environment, or be extinguished by astrophysical events. If the filter is future-facing, the silence becomes a warning mirrored in silence. Civilizations do not remain visible for long. Both interpretations are chilling in their ethical implications. One celebrates survival as a rare triumph. The other turns the absence of others into a cautionary tale about fragility. A third set of answers invokes deliberate discretion. The zoo hypothesis imagines that advanced intelligences choose to avoid contact, either to observe without interference or because contact would be destructive in unpredictable cultural ways. Alternatively, other civilizations might employ communication strategies utterly foreign to our expectations, using neutrinos, gravitational modulations, or engineering in higher dimensions that leave no detectable electromagnetic footprint in normal space. The idea of purposeful invisibility is hard to test because motive is epistemically slippery. It translates the scientific problem into a sociology of alien values. Temporal mismatch is another straightforward solution. Civilizations might flare briefly in cosmic terms. A species glowing brightly with radio or optical beacons for 1,000 years in the midst of a 10 billion year habitable epoch is a blink. The temporal overlap between two such flares separated by tens of thousands of light years is improbable. The galaxy is ancient. Humanity's radial era is momentary. The silence could therefore be a consequence of timing. Others may have existed and vanished long before our detectors listened, or they may arise long after. None of these broad classes of hypothesis is mutually exclusive. The explanatory landscape is a complex interplay of rarity, timing, preservation, and decision. What is crucial is that each hypothesis carries empirical consequences, constraints on what we should look for and where, and many of those consequences are testable in principle, even if the tests are difficult in practice. It is here that the story veers into deeper metaphysical terrain, the idea of a multiverse and the presence of hidden spatial dimensions. These frameworks alter not only probabilities but the very conditions that make life possible, and thus they can reshape the expectations embedded in Fermi's question. The multiverse is not a single theory, but a family of hypotheses that arise naturally in the best-selling chapters of modern cosmology and fundamental physics, eternal inflation, quantum cosmology, and the string theory landscape all produce cosmological pictures in which our observable universe is one patch amid an enormous, perhaps infinite, ensemble of regions, each potentially governed by different low-energy laws, constants, and particle content. In one pocket, the cosmological constant might be larger and prevent galaxies from forming. In another, the strengths of atomic forces might preclude complex chemistry. If the effective physical constants vary across the multiverse, then the apparent improbability of life in our empirical sample can be explained by selection bias. Observers find themselves in regions compatible with their existence. The anthropic principle, often used cautiously, becomes a probabilistic filter over the ensemble. That possibility eases some tension. If there are countless domains, then our universe's hospitable parameters need not be typical. They only need to be present somewhere. Yet this ease comes at a methodological cost. Many multiverse scenarios are hard to subject to direct experiment. Eternal inflation's pocket universes are causally disconnected. String landscapes enumerate vast numbers of vacua. Assigning measures, probabilities, across an infinite set is technically and philosophically fraught. The multiverse reframes Fermi's silence by diluting expectations in a vast meta-universe. Civilizations might be common in some domains and absent in most, and the fact that an observer finds themselves in a habitable bubble is unsurprising. But it also diminishes the predictive power of our inquiries unless observables that encode interactions between bubbles. Collisions imprinting subtle rings on the cosmic microwave background, or relic gravitational waves from bubble nucleation can be convincingly measured. Hidden spatial dimensions, on the other hand, emerge from the language of geometry and quantum physics in a way that is at once technical and imagistic. String theory, the most developed framework invoking additional dimensions, requires extra spatial directions for mathematical consistency. These additional dimensions are typically compactified, curled up into tiny shapes such as Calabi-Yau manifolds, invisible at everyday scales, yet their shape determines the spectrum of particles and forces in the effective four-dimensional world. The geometry of hidden dimensions therefore becomes a causal agent in the architecture of chemistry, the masses of particles, and the constants that control nuclear and atomic behavior. Slight changes in compactification can render chemistry barren or fertile. In that sense, the topology of unseen spaces is not idle metaphysics. It is a design parameter that can explain why some patches of the multiverse support life and others do not. Brain world scenarios, variants of string-inspired cosmology, add another evocative layer. Our familiar three-dimensional universe might be a membrane, a brain embedded in a higher dimensional bulk. Gravity might leak into the bulk, weaken our brain because it spreads its influence across additional dimensions. In such pictures, other brains could exist parallel to ours with their own physics and histories. Advanced civilizations might exploit the bulk, or they might find their expansions constrained to their own brain. Speculation about interbrain travel or hiding in extra dimensions quickly becomes metaphysical fiction at the level of detail. Yet as a conceptual move, it reframes the Fermi paradox. Perhaps other intelligences are abundant, but their activities are sequestered on other brains or in dimensions from which electromagnetic leakage into our brain is negligible. The result? Silence not from absence but from a mismatch of ontologies. These ideas are not merely whimsical. They produce empirical expectations that can be sought. Compact extra dimensions can lead to Kaluza-Klein resonances, heavier copies of known particles that could be glimpsed in high-energy collisions. Large extra dimensions would modify gravitational force laws at sub-millimeter distances, prompting precision tabletop measurements searching for deviations from the inverse square law. Bubble collisions between different inflationary regions could, in principle, leave circular anomalies in the cosmic microwave background's temperature map or a stochastic background of gravitational waves. At particular frequencies, none of these signatures has produced an unambiguous discovery yet, but the searches are real and the constraints tighten the space of plausible models. There is also a metaphysical wrinkle. If our universe's hospitable conditions are the result of a vast landscape of possibilities, then the Drake-like counting arguments must be reframed. The probability of intelligent life is not simply a product of local planetary factors. It is conditional on cosmological selection. The effective prior over habitable planets depends on how widespread favorable constants are across the landscape, and the expected number of neighboring civilizations becomes a joint function of local biology and global metaphysics. The anthropic reasoning that emerges is pragmatic but uneasy, balancing scientific restraint with a recognition that some explanatory moves, invoking selection effects across unobservable domains, skirt the traditional empirical character of physics. All of this returns the conversation to observational humility and methodological creativity. The implications for the search for life are manifold. A multiverse or hidden dimension framework can rationalize the silence by redistributing probability across inaccessible sectors, but it cannot, by itself, prove the absence of neighbors in our observable patch. Practical search strategies remain sensible. Survey the sky across multiple channels, catalog anomalies rigorously, pursue both biosignatures and technosignatures, and investigate the solar system for durable artifacts that might outlast atmospheric erasure. Simultaneously, particle physics and precision gravity experiments continue probing whether the foundations of space and time possess unexpected structure. The two strands, searching outward for evidence of others and probing inward for the architecture of reality, are complementary. Progress in one constrains the other. Beyond the technicalities, the emotional texture of this inquiry is striking. The Fermi paradox forces a posture that balances hope with patience, curiosity with epistemic modesty. The multiverse and hidden dimensions broaden the scale of humility. They remind humanity that what can be observed might be a tiny, lucky sliver of a vaster possibility space. The science becomes an invitation to enlarge the kinds of questions asked and the methods used, not a reason to give up. Finally, the interplay of these ideas connects back to the recurring theme of preservation and erasure. Just as geological processes can erase the traces of an entire civilization from a planet's surface, cosmological processes, inflation, causal horizons, and the stretching of space can conceal or obliterate relics of deeper histories. A multiverse populated with life does not guarantee that those lives leave durable, accessible records across the ensemble. In a universe where epochs, brains, and dimensions conspire to hide signals, the act of detection becomes an act of extreme patience and ingenuity. Silence is not merely a lack, it is a challenge that asks humanity to refine its instruments, its theories, and its philosophical frameworks. Fermi's question, then, remains both a practical puzzle and a provocative moral. Do we redouble the search for narrowband beacons and anomalous transits, or do we invest more in the experimental probes of space-time itself? The honest answer is both. The cosmos may be silent for reasons we will never fully resolve, or it may be silent because our ears are tuned to the wrong chorus. The pathways forward are empirical, theoretical, and reflective. They require better telescopes and deeper particle experiments, but they also require willingness to accept that explanation sometimes moves sideways, by changing the frame in which the problem is posed, rather than by pulling a single missing piece into place. In the end, the question is modest yet immense. Why, given time and matter, did intelligence arrive where it did, and, apparently, nowhere else within our ken? The multiverse and hidden dimensions offer explanations that widen the possibility space, but they amplify the demand for testable consequences. The Fermi paradox remains a lantern in the dark. It highlights the distance between expectation and observation, and compels a patient expedition into both the empirical sky and the hidden topographies of fundamental law. The silence is not a verdict. It is a summons to listen in more channels, to refine what counts as a signal, and to remember that absence of evidence is often evidence of absence only under assumptions that must themselves be scrutinized. What if the cosmos were held up by two pillars, not marble columns in some celestial temple, but parallel conceptual frameworks that, together, sustain the same observable world? And what if the world those pillars support were itself only a slender veneer, a slice of a far more capacious structure? These twin questions, about parallel descriptions of reality and the possibility that our universe is a thin, projected layer, arrive as one of the most disquieting and exhilarating ideas in modern physics, the holographic hypothesis and its relatives. The image is seductive and unnerving in equal measure. On one hand, humanity uses two very different languages to describe the same phenomena: the geometric language of space-time and gravity, and the algebraic language of quantum fields and information. For much of physics history, these languages were applied to different domains and rarely reconciled. Yet, over the past few decades, a surprising equivalence has been discovered in certain settings. A story told about gravity in a volume can be rewritten as a story without gravity on the boundary of that volume. These two narratives, bulk and boundary, curvature and correlation, are not merely analogous. In some rigorous models, they are mathematically equivalent. The discovery is astonishing because it suggests that what appears to be volume-filling reality might, at a deeper level, be redundant. The essential degrees of freedom live on a lower dimensional surface. That is the heart of the holographic principle. It grew from thinking about black holes. The realization that a black hole's entropy scales with horizon area rather than volume suggested that counting the degrees of freedom in a region of space might be proportional to the area that bounds it. From a thermodynamic standpoint, it implied an economy. The information content of a region is limited by its boundary. The radical leap, to imagine that the universe itself might be encoded on a distant boundary, followed naturally once that kernel of compression was seen in black hole thermodynamics. Adds CFT duality, the most concrete embodiment of the idea, provides a playground in which a gravitational theory in anti-de Sitter space is exactly dual to a conformal field theory on its boundary. In this setting, geometry and quantum fields are two faces of the same coin. The emotional texture of this discovery is peculiar. There is awe at the elegance of the equivalence and exhilaration at the calculational power it provides. Yet there is also vertigo. If a full quantum gravitational description can be encoded on a lower dimensional surface, then questions about what is ontologically primary become slippery. Which description is the ground reality? Does the bulk exist independently, or is it a convenient, emergent theater conjured by correlations on the boundary? The very idea stretches the imagination. The things that feel most real, spatial volume, curvature, three-dimensional locality, could be emergent phenomena, not fundamental givens. This conceptual tension has practical consequences. The holographic viewpoint offers a promising route to resolve long-standing paradoxes, particularly the information puzzle of black holes. If gravity in some region is dual to a non-gravitational quantum theory on its boundary, then unitarity, The requirement that information is conserved in quantum mechanics is automatic in the dual description. From the boundary's vantage, evolution is manifestly unitary. The black hole's apparent thermal evaporation becomes a process, whose information accounting is explicit. In that way, the holographic pillar can absorb contradictions that haunted the bulk-only picture. But the hologram idea also invites bolder speculation. Might our entire observable universe be a thin slice in a much larger ensemble? Two families of thought converge here. One is brain world cosmology, inspired by string theory. It imagines our familiar three spatial dimensions as a membrane, a brain, embedded in a higher dimensional bulk. The particles and forces we experience would be trapped on that brain, while gravity could leak into extra dimensions. In such pictures, the universe that humans inhabit could be literally a sheet within a broader geometric tableau. The other family is more radical. Suppose the true description of reality is holographic, defined on a boundary that lies at cosmological infinity, and what we perceive as depth is an emergent pattern on that boundary. In either case, the familiar sense of being surrounded by three-dimensional space becomes provisional. These ideas are not mere philosophy. They produce concrete, if difficult, empirical consequences. Extra-dimensional scenarios can alter the strength of gravity at very small distances. They can produce heavier copies of known particles, or modify early universe dynamics in ways that leave subtle imprints on the cosmic microwave background or on gravitational wave backgrounds. Holographic approaches recast singularities in the Big Bang in new terms, sometimes replacing the catastrophic breakdown of geometry with transitions in the dual theory. The hopeful promise is that the paradoxes spinning around singularities' horizons and information loss might be softened when reinterpreted through a dual description. And yet, with all their elegance, these proposals introduce epistemic limits. If the true degrees of freedom lie on a surface infinitely removed from our intuitive notion of inside, then direct evidence becomes inherently indirect. Observables are still anchored in the local physics of galaxies and particles, but the mapping from boundary to bulk may be highly non-trivial. The search for smoking gun signatures becomes a layered enterprise. One must identify predictions that distinguish holographic or brain world models from conventional scenarios, and then push instruments to the precision where those differences are measurable. Beyond technicalities, the conceptual landscape prompts a philosophical return. What counts as real? If space-time and locality are emergent, then reality's deepest layer may be informational rather than material. The language shifts from fields and curvature to entanglement patterns and algebraic relations. In this sense, the two pillars, geometry and information, are complementary descriptions. Each is indispensable for certain questions, and each frames the other. This intellectual architecture slides naturally into the next mystery, one that blurs physics and philosophy. Is there any meaningful link between consciousness and the fabric of the cosmos? Do the same informational structures that might underlie space-time also play a role in minds that observe, measure, and narrate? It is a question that blends metaphysics and method. On one level, the connection is obvious and modest. The existence of conscious observers is a necessary condition for questions about meaning and measurement. Without beings capable of registering outcomes and forming memories, there would be no narratives, no scientific inferences, and no human-scale puzzles. On a deeper level, the inquiry becomes speculative and contested. Some thinkers have proposed that consciousness is an emergent byproduct of complex information processing systems. Others suggest it may be more primitive, perhaps woven into the fabric of reality in a panpsychist or proto-conscious manner. A third class of proposals links consciousness to quantum processes, arguing that certain quantum coherent states might be necessary for subjective experience. None of these positions is established science. Each is a philosophical hypothesis with varying degrees of testability. Consider first the pragmatic stance, consciousness as an emergent property. From this perspective, conscious experience arises when systems achieve certain functional thresholds in information integration, memory, and predictive modeling. Theories like integrated information theory, it, attempt to quantify aspects of experience by measuring how much a system's causal structure constitutes irreducible integrated information. While mathematically precise in its own terms, IIT faces empirical and conceptual challenges. How to map abstract measures to biological brains, whether the theory attributes consciousness in counterintuitive situations, and how to test its predictions across differing substrates. Still, the virtue of the emergent perspective is methodological modesty. It treats consciousness as a phenomenon contingent on organization, not a fundamental addition to physical law. By contrast, proposals that place consciousness as fundamental, either through panpsychism or through bold physical hypotheses, reorient the debate. If proto-conscious qualities are basic constituents of the universe, then the explanatory problem is inverted. Complex brains are organized amplifiers of ubiquitous experiential twitches rather than novel births of subjectivity. Such views can be formulated in careful philosophical terms, but they risk sliding into metaphysical arbitrariness unless anchored by testable predictions. They do, however, offer a conceptual bridge to information-centered views of physics. If the substrate of reality is informational, and information has intrinsic experiential character, then the divide between observer and observed narrows. A different strand, and the one that most often receives attention in popular accounts, ties consciousness to quantum mechanics. The measurement problem in quantum theory invites questions about the role of observers in collapsing superpositions into definite outcomes. Historically, some interpretations lent a special role to conscious observers. More recently, decoherence-based accounts explain apparent collapse as a consequence of entanglement with environments, without invoking mind-centric causation. Still, the allure persists. If mind and measurement cohabit the same conceptual territory, could consciousness be implicated in physics at a foundational level? The contemporary scientific posture is cautious. Decoherence, quantum information theory, and advances in neurobiology strongly suggest that consciousness does not perform miraculous physical collapses. Yet the measurement problem remains open in interpretational terms, and that openness leaves a slender alley for speculative connections. If space-time is holographic, if the bulk geometry emerges from patterns of entanglement and information on a boundary, then the question of consciousness invites one more provocative conjecture. Could subjective experience be related to particular informational architectures that also give rise to geometry? In other words, if entanglement builds space and certain patterns of information underpin minds, might there be a non-accidental resonance between the two? The idea is tempting, but it moves quickly from metaphor to risky assertion. The absence of evidence that subjective states have causal power at cosmological scales, combined with the enormous gap between neural information processing and cosmological entanglement, urges caution. The more defensible claim is epistemic rather than ontological. Conscious agents are the only entities in the universe so far known to construct narratives and test hypotheses. Therefore, any account of cosmology must reckon with the constraints and selection effects that observers impose. This epistemic angle brings the conversation back into method. A universe with observers is not just a physical system. It is a system in which measurement, record-keeping, and question-asking are possible. That fact has formal consequences. Quantum cosmology must grapple with how to define probabilities when observers are included within the system being described. Anthropic reasoning, the observation that only certain regions of parameter space admit observers at all, thus reappears in a subtler guise. The presence of consciousness does not perforce change the laws of physics, but it shapes the conditional probabilities of observing particular features of the world. There is also a human, emotional dimension to the debate. The notion that mind and cosmos might be linked is provocative because it speaks to longing as much as curiosity. The idea that human subjectivity might be exceptional in the cosmic ledger is a temptation that science resists because it forces unwarranted hubris. Yet the complementary idea that human minds are diminutive and contingent can be bleak in its effect. The productive stance lies between extremes. Humility about human centrality combined with appreciation for the singular cognitive capacity to pose these very questions. That cognitive capacity is itself a product of cosmic history, the synthesis of nucleosynthesis, star formation, planetary habitability, and biological evolution. In that sense, consciousness is a consequence, not a cosmological cause. Importantly, the search for empirical contact between mind and cosmos is not hopeless. Neuroscience, cognitive science, and physics intersect in areas where information theoretic measures can be operationalized. If certain physical substrates reliably generate specific informational signatures associated with conscious processing, and if those signatures have unique testable consequences, then empirical progress is possible. Conversely, if no link between cosmological scale informational structures and neural computation can be established, the bridge remains conceptual rather than causal. The most robust philosophical lesson to be drawn from the discussion is methodological restraint, the universe's architecture. whether supported by parallel pillars of geometry and information, whether holographic, whether embedded as a thin slice within a higher dimensional bulk, is a question for physics and mathematics. The nature of consciousness is a question for biology, cognitive science, and philosophy. The two domains can inform one another. Physics sets the conditions of possibility for life and cognition. Cognitive science clarifies what counts as an observer and thus how to frame epistemic selection, but conflating the domains risks speculative overreach. Good science proceeds by proposing models that make testable predictions and by accepting that some deep questions may remain recalcitrant for a long time. Still, the union of these themes is one of the most poetic features of contemporary inquiry. Humans, petty and temporal and spatial scale, have constructed conceptual ladders that reach toward the deepest architectures of reality. The thought that the geometry of space itself might be a shadow of information on a far boundary, or that consciousness is an emergent pattern of organized information, does more than provoke curiosity. It reframes the very notion of what it means to know. The hope is not for triumphant closure, but for a slow accretion of constraints, new calculational tools, sharper experiments, more precise maps of the cosmic microwave background and gravitational wave backgrounds, laboratory probes of miniature gravitational behavior, and deeper integration across disciplines. For now, the questions remain. Is the cosmos a thin projection of a larger structure? Are parallel pillars, geometry and information, simply two dialects of a single reality? Does consciousness participate in the universe's architecture, or does it stand aside as a consequence of cosmic happenstance? The best response is both scientific and human, to continue with patient experiment and rigorous thought, and to hold these questions with a mixture of modesty and wonder. In that tension, between bold conjecture and disciplined skepticism, lies the work that will occupy generations, building instruments, refining mathematics, and learning, as the archive of deep time is slowly read, whether the world is thicker or thinner than it feels, and what role, if any, minds play in the tale. What would it mean to discover that the cosmos carried something like awareness? The question arrives like a single lucid image, not a deity peering down from a throne, but a web of relations in which information, organization, and responsiveness are woven so deeply into the fabric of reality that the distinction between mind and world becomes porous. It is a hypothesis that sits at the border of science and philosophy, and it forces a rethinking of the very categories matter, law, information, meaning that have guided inquiry for centuries. The history of human thought offers two persistent counterweights. On one side lies a long tradition that treats the universe as a mechanism, cold, lawful, describable by equations that do not care whether there is a thinker to read them. On the other side lies the older, almost instinctive tendency to animate the world. Rivers have moods, storms carry messages, mountains keep counsel. Between these poles, the modern scientific imagination has built its scaffolding, a commitment to empirical regularity, to testable inference, to explanations that conserve energy and make predictions. The core question, then, is methodological as well as metaphysical. Can the idea that the universe has a depth of consciousness be rendered into a scientific hypothesis, one that yields empirical consequences and thus can be treated like any other claim about reality? There are at least three pathways by which the question moves from the armchair into the laboratory, each with its own set of promises, pitfalls, and emotional textures. The first is the informational turn. Over the last few decades, the language of information has seeped into every corner of physics. Entropy was reinterpreted not simply as disorder, but as missing information about the microstate of a system. Quantum mechanics was recast in the vocabulary of qubits and channels. Holography proposed that the degrees of freedom inside a region could be faithfully represented on its boundary. That geometry itself might be an emergent story told by entanglement patterns. From this vantage, it is natural to ask whether information processing is the substrate of reality. If space and time emerge from entanglement, and if entanglement is a form of relation among underlying degrees of freedom, then the universe might be best described as a vast, ongoing computation. That reformulation is not the same as asserting that the cosmos is conscious in any human-like sense. Information is ubiquitous and indifferent. A thermodynamic engine processes information, as does a weather system, and neither requires a subjective vantage. Yet the informational framing does slide the conceptual furniture. It suggests that the most primitive language for describing nature might be informational rather than material, bits and correlations, not blocks of matter. From there, a subtle anthropic temptation emerges. If consciousness in brains correlates with certain patterns of information, integration, and complexity, could those same patterns, at vastly different scales and substrates, instantiate forms of proto-experience? The debate here is fierce and patient. Integrated information theory and related formalisms make concrete proposals about which systems could possess degrees of phenomenal structure. Critics respond with requests for empirical discriminants and with caution about anthropomorphism. The second pathway connects consciousness and quantum foundations, quantum theory's measurement conundrums, thought experiments such as Wigner's friend, and choices about when a superposition becomes a definite outcome, have historically invited proposals that invoke observers. Some early interpretations lightly flirted with the idea that consciousness played an active role in collapse. Modern developments, driven by decoherence theory and the pragmatics of experiment, have largely displaced observer-centric collapse from the mainstream. Decoherence shows how entanglement with an environment yields effectively classical outcomes for local observers, without requiring mind to punch a hole in the mathematics. Still, at the fringes, the measurement problem leaves open conceptual gaps. Questions about the ontology of the wave function, about whether probabilities are epistemic or objective, and about the role of the observer in specifying an experimental context remain unresolved in a way that invites philosophical speculation. The crucial methodological demand here is exacting. Any assertion that consciousness has a special causal role in quantum outcomes must predict laboratory effects distinguishable from the standard decoherence picture. To date, the experiments have been unyielding. When laboratories control for all classical sources of noise and measure ever larger quantum systems, the appearance of classicality follows the expected patterns of decoherence. That empirical resistance has not ended the conversation, but it has pushed it towards subtler questions of where and how a hypothesis about mind as physical cause could be tested. The third pathway is metaphysical: panpsychism, neutral monism, and related positions. These ideas do not posit that rocks and stars possess full human consciousness. Rather, they suggest that the basic constituents of reality carry proto-qualities that can be combined in complex organizations to yield rich, subjective life. The attraction of such views lies in their economy. They attempt to avoid the troubling emergence gap, the leap from inert particles to qualitative experience, by inserting a minimal experiential grain at the bottom of the ontology. Philosophically, panpsychism reframes the explanatory burden. Instead of explaining how matter spawns mind, it explains how mind arranges into the degrees of unity we recognize in persons. From a scientific standpoint, the difficulty is twofold. First, panpsychism risks slipping into unfalsifiable speculation unless it articulates mechanisms by which proto-experiential properties manifest in measurable correlations. Second, it must confront the compositional problem. How do billions or trillions of tiny experiential bits combine into unified, reportable consciousness? Theoretical proposals grapple with these issues, but they remain contested. The empirical strategy is therefore indirect. Test whether functional theories of mind, those grounded in neurobiology and information processing, suffice to explain human and animal cognition. Where those accounts stall, panpsychic models have narrative room to maneuver. Where neural functionalism succeeds, panpsychism loses its explanatory advantage. Throughout these debates, the emotional undertow among investigators is striking. There is awe at the possibilities, a vertiginous recognition that the categories used for centuries might be misstated, and a chastened patience in face of the difficulty of designing decisive experiments. Scientists speak in two voices. One is the engineer's voice: build more precise instruments, refine protocols, expand observational reach. The other is the poet's voice: imagine how different metaphors, organism, computation, tapestry redraw humanity's picture of place and meaning. Both voices coexist because the question is both technical and existential. The implications are vast and practical. If the universe has no intrinsic cognitive depth beyond the emergent cognition of complex structures, then the project of understanding remains a matter of decoding physical law and the contingencies of history. If, by contrast, there is a deeper layer in which information and responsiveness constitute the reality's fabric, then the scientific enterprise expands. Physics must account for new primitives. Biology must learn to map phenomenality onto organization, and ethics may recalibrate in response to newly recognized forms of value. But the route from metaphysical discovery to moral obligation is not straightforward. Recognition that certain systems have proto-experience would not automatically dictate moral parity with human beings. Degrees and kinds of subjective complexity vary. Ethical frameworks would need to be proportionate to those differences. Importantly, the inquiry into cosmic cognition does not stand alone. It folds back into the other puzzles explored earlier: the jigsaw of lost civilizations, the secrecy of dark matter, the inscrutability of dark energy, the fate of information in black holes, and the silence recorded in Fermi's question. Each of those problems is also about what can be known and what is preserved. The same constraints, horizons, erasures, selection effects, govern the detectability of mind-like processes at planetary, galactic, or cosmological scales. A civilization's cultural record can vanish under tectonics. A cosmological signal can be redshifted into unobservability. Entanglement structures can be inaccessible behind horizons. The question of whether the universe has cognitive depth is thus constrained by the same empirical limitations that have been refrained through the whole narrative of deep time. Where does that leave the open question? Is the universe purely physical, or does it possess a depth of consciousness? The honest, scientifically responsible position is provisional humility. There are plausible reframings of physics that treat information as primary, elegant formalisms that suggest geometry emerges from entanglement, and thought experiments that show how consciousness-related ideas might map onto formal structures. Yet the hard empirical muscle has not flexed a definitive answer. The available data do not demand that consciousness be a fundamental constituent, nor do they rule it out. The frontier is not absent of landmarks. It is crowded with signposts pointing to promising experiments and clarifying models. Those signposts are concrete. They include tighter tests of quantum foundations that push coherent superpositions to macroscopic scales, refined measurements of cosmological signatures that could reveal whether information is conserved in subtle ways at horizons, and neurobiological research that correlates specific information architectures with robust markers of subjective processing. They also include conceptual work, sharpened criteria for what would count as evidence that a system manifests anything like experience, and rigorous methodologies for distinguishing between functional complexity, behavioral competence, information processing ability, and subjective interiority, phenomenal character. If anything, the meditative core of the inquiry is ethical as much as empirical. The posture required is not romantic openness to any fanciful hypothesis, nor rigid scientism that rules out imaginative alternatives by decree. Rather, it is the patient curiosity that has run through the larger project traced here: assemble fragments, respect the biases of preservation, build instruments to extend vision into the dark, and accept the provisionality of even the most cherished conclusions. The question about cosmic cognition is an invitation to methodological pluralism, sustain precise experiments, cultivate rigorous conceptual distinctions, and remain alert to the social and moral dimensions of the claims being made. Part 12. Conclusion: The Borderlands of Knowledge. At the end of a long survey, the most honest picture is a map of boundaries. The cosmos presents not a single impenetrable wall, but an archipelago of frontiers, horizons beyond which direct observation is impossible, scales where current theories fail, archives erased by time's erosion, and conceptual gaps where language strains to hold the idea it intends to convey. Those borders are not failures of human intelligence. They are contours that shape where curiosity may move next. Each mystery encountered in the preceding chapters is a lesson in humility. The absence of ruins from an ancient civilization is a lesson in geophysical contingency. The singularity at a black hole's core is a lesson in theoretical breakdown. The silence asked by Fermi is a lesson in temporality and selection. Dark matter and dark energy are invitations to expand the taxonomy of physical entities and to refine the methods by which existence is inferred. The arrow of time insists that narratives can be told at all, even as it reminds that records are fragile and ephemeral. Holography and the informational turn provide new grammar for the same stories, while the question of consciousness reframes the stakes of inquiry. The response, repeated across many domains, is methodological. Build instruments that extend perception. Invent theories that produce testable consequences, cross disciplinary borders so that insights from one domain shed light on another, and cultivate an epistemic humility that recognizes provisionality as a virtue rather than a defect. The future of knowledge is not a single triumphant theorem, but an accretion of constraints, corrections, and occasional revolutions. It is the slow tightening of a net around reality that, in the process, refines what is meant by explanation. There is also an ethical and cultural charge. Knowledge changes the terms of stewardship. Understanding the fragility of evidence over geological time argues for the preservation of what can be preserved: archives, cultural memory, planetary environments. The recognition that observational windows are finite, that cosmic backgrounds fade, that technological signals are ephemeral, presses an urgency on the work of recording and conserving human achievement. The sciences of deep time are not ivory tower pursuits. They are acts of testimony designed to keep a conversation across epochs. Finally, there is the emotional register that has run through the whole exploration, a mingling of awe, vertigo, and consolation. Awareness of vast scales and deep epochs produces smallness. Knowledge that the ledger of the past is partial produces unease. The discovery that patterns can be discerned from fragments produces exhilaration. The posture appropriate to that mix is a patient courage, curiosity without hubris, ambition without presumption, and an acceptance that some riddles will be with us for generations. The border of knowledge is not a closing gate. It is a thin, luminous ridge where questions sharpen into new instruments and where imagination meets constraint. It is the place where hands keep assembling the jigsaw, where telescopes and spectrometers and deep mines and underground detectors are built, where mathematics invents new languages, and where disciplines talk to one another, because reality refuses to be parceled neatly into departments. In that spirit, the work is straightforward and enduring. Continue to refine the maps of what is visible. Continue to expand the modes of what counts as evidence. Continue to treat anomalies with a patient mixture of hope and skepticism. Continue to acknowledge that absence can be as informative as presence when its assumptions are explicit. Continue to protect the fragile archives that permit future minds to reconstruct the past. The project is not an accumulation toward finality, but a practice of stewardship across time. It is the labor of listening to a cosmos in which signals are weak and errors are long, and of shaping the instruments of inquiry so that they resonate with the faintest whispers. The borderlands of knowledge are where the next generation of questions will be born. They are where the next acts of courage, engineering, measurement, philosophical daring will refine the contours of what it means to know. So the story pauses here, not because the questions are exhausted, but because they have become sharper. The universe still offers fragments, photons stretched to infinity, isotopic ratios whispering of vanished climates, entanglement patterns hinting at emergent geometry, and the thin, improbable flame of cognition on a pale blue planet. Each fragment is a promise and a limit. Together they form a mandate to keep asking, to keep measuring, and to keep bearing witness. The border between the known and the unknown is where humanity has always stood. There, with tools in hand and humility in heart, the work continues. Consider the unresolved as a door left slightly ajar, a narrow seam of darkness against the wall of knowledge. Its hinge warm from years of inquiry, its handle pressed by the collective curiosity of generations. That image is not ornamental. It is the most honest metaphor for the state of things at the end of a long survey of origins, endings, and the many mysterious places in between. Each unresolved question is not a failure of intellect, but an invitation, a threshold that, if gently pushed, swings wide into a new chamber of complexities, surprises, and subtler mysteries. The paradox is simple and exact. The closer the approach, the more the universe refuses to be exhausted by a single answer. Instead of revealing closure, each step forward reveals new layers, folding the panoramic into the intricate and insisting on two virtues at once: humility for what remains unknown and patience for the time it takes to discover what can be known. This is not a consolation for ignorance. It is an ethic of inquiry, the archive that humanity reads incomplete in ways that are not accidental but structural. Geological processes erase, cosmological expansion redshifts, quantum fuzz hides, and horizons place principled limits on what can be observed. The consequence is a methodology that prizes careful inference, integrative thinking, and the slow patina of corroboration. When a subtle, spectral line appears in an exoplanet's atmosphere, when a faint ripple in space-time is heard, when a pattern of isotopes hints at climates long gone, the first feeling is exhilaration. Yet that exhilaration is immediately accompanied by a disciplined skepticism. What might mimic this signal? What preservation biases shape its survival? Which alternative explanations must first be discarded? Those twin currents, wonder and rigor, are what carry inquiry forward. Approaching the ajar door of the unresolved, one sees the same choreography played at many scales. The detection of gravitational waves did not end the study of strong gravity. It opened a corridor into the dynamical, non-linear language of space-time. The mapping of the cosmic microwave background did not complete cosmology. It supplied a coarse-grained canvas that then required finer brushes, searches for primordial gravitational backgrounds, non-Gaussianities, and the imprints of bubble collisions. The null results of decades-long particle searches for dark matter were not a defeat. So, much as a redirection, what had seemed like the likely particle paradigm branched into axions, sterile neutrinos, primordial black holes, and even into the possibility that gravity might require modification on very large scales. In each case, the pattern is the same. Explanation begets new diagnostics. Diagnostics expose deeper unknowns. That pattern is not merely intellectual. It shapes the emotional architecture of scientific work. There is a peculiar kind of hope that is not naive optimism, but engineered patience. Researchers calibrate ambitions against the long arcs of instrument development, funding cycles, and the inevitable setbacks of null results and false positives. Laboratories, telescopes, and deep-field probes are instruments of patient listening. They convert impatience into design cycles, false starts into methodological refinement. The community develops rituals of verification, independent replication, blind analyses, cross-checks across wavelengths and methods. These rituals are not bureaucratic. They are moral practices that protect the collective story of how knowledge advances, and they are the practical means by which the door remains open, rather than slammed shut by premature certainty. There is, too, a pedagogy in the way mysteries reveal themselves. The jigsaw of planetary deep time teaches that absence is not a clean shelf. It is a scarred and biased surface. The paradox of missing civilizations on geological timescales is not a prompt for fantastical narratives, but a prompt for disciplined inference about preservation bias. A thriving coastal culture can be swallowed by rising seas, its pottery ground into sand, its structures subducted and metamorphosed. An energetic technological civilization may broadcast for a century and then return to silence under ash, ice, or deliberate deletion. These are not metaphors for futility. They are practical reasons to diversify the modes of search. Telescopes for techno-signatures, spectrometers for biosignatures, archaeological strategies that look for geochemical anomalies, and renewed attention to the durability of material traces. The moral imperative to preserve the present follows naturally. The finite legibility of evidence in deep time is a public good. Archives, both physical and digital, are fragile. Geological processes will not be kind to the paper and glass that carry this moment's culture. The ethic of stewardship framed by the study of deep time is therefore plain, archive intentionally, distribute widely, and think about redundancy across epochs. In scientific practice, this means not only making data public and reproducible, but preserving physical specimens, replicating instrument designs, and ensuring that methods and metadata survive institutional turnover. The act of recording is itself an act of trust in the future, an acknowledgement that discoveries will be made and that they will matter to minds the present can barely imagine. Humility also extends to the limits of theorizing. The great explanatory frameworks, general relativity, quantum field theory, thermodynamics, are immensely successful within their domains. They carry with them boundary markers. Singularities, for instance, are not just curiosities. They are explicit statements that the descriptive framework has reached its edge. In those regions, asking the same questions in the same terms is a category error. The more the community probes with gravitational waves, horizon-scale imaging, and delicate measurements of black hole environments, the more constraints appear that direct theoretical creativity, holographic dualities, quantum corrections to semi-classical pictures, and entanglement-based reconstructions of geometry. Each framework replaces one set of puzzles with another, but it does so in a way that allows testable predictions. The lesson is pragmatic. Cosmological boldness must be held accountable by observational imaginings that produce falsifiable expectations. Patience is not passive. It is a strategic stance toward cumulative evidence. Instruments must be built to reach subtle thresholds. Collaborations must be sustained across decades. Theories must be refined to the point where their predictions can be contrasted. When dark energy was first inferred from supernovae, the response was not a chorus of immediate models, but a broad program of measurement, map baryon acoustic oscillations, measure weak lensing, refine distance ladders, and build space telescopes tuned to subtleties of the cosmic geometry. The value of that program is not in quick victory, but in the slow collapse of uncertainty into constraint. The patience that science cultivates is the discipline of allowing instruments and data to do their work. While theory remains an active interlocutor rather than a mere arbiter of taste, there is also a social dimension. The hinge of the door is communal. The perseverance required to explore deep-time mysteries cannot rest on heroic individuals alone. It depends on institutions that endure, training that passes methods across generations, funding models that accept long investment horizons, and cultures of openness that welcome critique. This is why big projects, telescopes, particle detectors, space missions are social feats as much as technical ones. They consolidate expertise and distribute risk. They are exercises in collective patience, building machinery that will speak only after years, sometimes decades, of quiet operation. The closing chapters of inquiry are rarely dramatic in the sense that news headlines suggest. Rather, they are accumulative. A marginal detection becomes clickable as a pattern in many datasets. A theoretical idea becomes persuasive when it organizes otherwise disparate anomalies into a coherent narrative that survives rigorous attempts to falsify it. This accretion is what transforms a door ajar into a threshold confidently crossed. Rarely does a single observation suffice. Usually it is the chorus of consistent, independently produced evidence that convinces a community to update its map of reality, and yet the world insists on remaining generous with the unexpected. The more that is learned about the cosmos' deep structure, the behavior of dark sectors, the dynamics of vacuum energy, the quantum underpinnings of space-time, the more the structure seems to invite further questions. This is not a recursive trap, it is the natural shape of a reality that is layered and hierarchical. To approach a fundamental layer is to encounter instruments and methods that are sensitive to phenomena at that scale. And those instruments often reveal phenomena that were invisible at coarser resolutions. That is the good news. The unresolved is not a closed gulf. It is a corridor into new techniques and new mathematics, and the cumulative expansion of observational reach will, in time, push the door wider. There is a moral and political urgency that follows from this intellectual humility. If evidence is time-dependent, if windows close as universes expand and archives erode as geology moves, then some knowledge is perishable. It follows that certain empirical projects are time-sensitive in ways that demand prioritization. Preservation of cultural heritage and the systematic cataloging of astronomical phenomena are both acts of responsibility. That does not mean crisis-driven frenzy, but rather a sober triage of research priorities. Invest in instruments that can capture fading cosmic backgrounds, in subterranean detectors that will continue to test dark matter parameter spaces, and in planetary reconnaissance that can find durable traces in the solar system before natural processes rework them. The future is not merely theoretical, it is infrastructural. Finally, the temper of curiosity that best suits the open door is ethical as much as intellectual. Curiosity accompanied by hubris tends to rush, to insist on premature closure, and to promote elegant but untested narratives. Curiosity accompanied by humility pauses, listens, and redeploys effort where it will most increase the long-term legibility of evidence. That posture is not defeatist. It recognizes that the universe is both generous and stealthy. It offers signals, but those signals often require patient, multifaceted attention to reveal their meaning. So the door remains a threshold of possibility, each tentative step through it. Whether a new probe of the microwave sky, a refined particle search, a deeper gravitational wave catalog, or a careful archaeological survey, promises not finality but richer landscapes. The closer the approach, the more the universe opens into strata of deeper subtlety, patterns of correlation where once there were only isolated facts, new forms of evidence where once there were only shadows, and more sophisticated concepts where primitive metaphors will no longer suffice. To cross such a threshold responsibly is to accept that every answer will be partial, that every model will be provisional, and that the act of understanding is an ongoing exchange between instruments, theory, and the public commitments that sustain them. The unresolved, then, is not a wound to be closed at once. It is a door waiting to be opened with care. The work at that door is the practice of patient, disciplined curiosity, the building of durable instruments, the stewardship of fragile archives, the cultivation of cross-disciplinary vocabularies, the ethical recognition that knowledge is a generational trust. Approaching the threshold requires both humility, an acknowledgement of limits, of erasure, of provisionality, and perseverance, the long collaborative labor of building the capacity to see what has been hidden. Together, those virtues keep hands on the handle. The universe yields its depths slowly. When it does, the revelations do not diminish wonder, they deepen it, and they demand a corresponding expansion in the wisdom with which humanity stewards the knowledge it recovers. So the story pauses, not because the door has been shut, but because it stands ajar, the darker side of the frame lit with possibilities. The next generations will push gently, listen, and sometimes have to wait while instruments mature and theories sharpen. When new chambers reveal themselves, they will contain puzzles as beautiful and humbling as those just passed. That is the nature of the threshold. Every opening is also a promise that the map will lengthen and that the hands at the table must remain patient, persistent, and modest. The unresolved is, in truth, an invitation, not to final answers, but to the kind of slow, steady work that befits creatures brief in cosmic time but boundlessly curious.